Okay, good evening, everyone. We can start the session right now. So I'll share my slide. I hope it is visible. Tajul, can you once more confirm?
Yes, sir, it's visible.
Oh, okay, fine.
Yes, sir, it is visible. Thank you.
Thank you. Um, Now I have switched off my video just because I'm in Delhi right now, and kindly let me know if my voice is inaudible in between or anything. I can repeat my session a bit part. Uh, once again. Now, in the last particular lecture, when we talked about moment resisting frame and IS 18168, I had told you, this is just a recap. I had told you that we are using the capacity based design procedure for our analysis, wherein we use capacity design to get the seismic demand or the forces in the system. Let it be beams, columns, or in that system. And once we get the analysis forces, we design as per limit state method of IS 800 2007, right? So we talked about the beams being the deformation controlled element in the moment resisting frame and columns being the force controlled element. We use capacity design procedure to assess what is the maximum capacity that the beam can transfer, the deformation controlled element, which is the most ductile element that can be transferred to the force controlled element, and we use that particular capacity design procedure to assess the maximum forces and then use the limit state method to design the columns for the assessed forces, right? Then we talked about protected elements, which is like the area where the plastic hinges are most probable to get formed, which is the beams may, if you remember the clause, it says 2 dB, which is 2 times the depth of the beam. That is the region at the ends of the beams where the plastic hinges will form, which is known as a protected zone, and that particular zone has to be kind of protected from all infringement in terms of nothing should be welded, no cutout should be brought in the element there, because it has to be kept pristine. The next thing that we learned about is, okay, we in the protected zone, we should not be considering the composite action of this slab. So there will be no shear studs that will be provided in the location where the plastic hinges are getting formed. That is to ensure that there is no asymmetrical hysteresis curve that is getting formed, which causes a premature failure of the beam element rather than the delayed one, which occurs due to if we don't consider, if the only the beam and not the slab is coming into picture when the beam undergoes cyclic loading during earthquake, right? The other part we learned about is the panel zone. The code wants, our 18168 says we need some kind of limited yielding in the member, but as explained in last particular moment resisting frame, we understood that even though it says it has to be used, there is no particular achievement, a particular target in terms of how much the limited value is to be quantified as. So it is ambiguous state, and mostly by the time we come up with the design, it may be a kind of what do you say, an elastic panel zone that will be ended up, right? And the other things that we understood is that the overstrength factor that we get in a steel frame system, in an RCC system, after we design and if we assess, let's say by pushover analysis, we get an overstrength of 2.53 or on a value. It's not a hard line value that I'm saying, but in case of steel structures, the overstrength that we get is of the range of 6 to 10. And why that happens so is because not just the strength criteria, yes, the drift also, moment resisting frame is governed by drift rather than the strength because its stiffness is very low. Other than that, the compactness ratio of the element also becomes the non-availability of sections also affects the system, the final size of the sections that are getting put in the system, then strong column weak beam ratio. So these, other than the strength and drift criteria, these other criteria also come into play, and overall it enhances the size of the beams and columns you end up in the system, which enhances the overstrength in the system, right? So this is overall in a nutshell what I taught you last time. And most of the concepts in terms of capacity design based design assessment will be taken forward to the CBF system and EBF system. Understand that once the forces are, today I'll explain to you. CBF is a very tricky kind of a design. So once you understand how, where the capacity design comes in, And where limit state method comes in, it will be all clear. Like once again, I'll say capacity design, we identify a particular element which is going to be the fuse, like electrical fuse in the system, which will undergo nonlinear deformations. It will dissipate the energy, protecting the force controlled element, which will be the other system that will be governed by forces which comes from these fuse elements. So we have to design the force controlled element for the maximum forces that comes from these deformation controlled or the fuse elements that come into picture, right? Starting today's lecture, we'll start with concentrically braced frames. Now, concentrically braced frames, you can see the images here on the left. These are different types of concentrically braced frames. You can see in an industrial structure, you have the concentrically braced frame here. What do we mean by concentrically braced frame is if I draw a center line of the beams, columns, and braces, it will intersect at one particular point. And in an EBF system, it is eccentric. We'll come to EBF system at the later part of this particular lecture. This is a mega brace frame, which means the braces that are there ties different floors together. It is not between one single floor, as it is in this particular case, but it ties different floors together. So it can be how can we assess or how can we design or how can we see the CBF system is as a vertical truss system. Like this is a truss system, we can think of it, right? Now, earlier cases or in cases where you go for a warehouse design or something like that, earlier the braces were not designed for seismic forces. Somebody is speaking. Tajul, can you mute the participant? Okay. So earlier, how the frames were being designed were like कि अगर braces आप दे रहे हैं तो it is like mostly like for wind design and all, and you understand that if your warehouse like structure is being governed, I mean the load combinations are such that only the wind forces govern the design. Then if you give a brace, then this fuse concept or ductile design, nothing comes into picture. That particular brace has to remain elastic throughout under wind forces, and that is how things were designed. So till 1970, seismic provisions for brace frame never came in through in the US. But once 1994 Northridge earthquake, which we talked about last time in terms of how that became the pivot for many design improvisation, many codal clauses that came into being, came after 1994 Northridge earthquake and one more 1995 Kobe earthquake. These two earthquakes or this two timeline, 1994 and 1995, have been very pivotal in terms of steel design that we do now, right? And till now also, okay, is it clear now? Tajul, is my voice okay?
Yes, sir. Yes, voice is clear.
Okay, okay. The amount of experimental investigation, like moment frames, we learned that in 1880s, the Chicago building came in. A lot of connection designs were done, tested, validation. So many studies have been done on moment resisting frames. But in CBF system, it is relatively new. So the amount of research that has been done in terms of experimental and numerical are very low. Now, this particular slide is important to understand. Like this is the point where we understand in this particular CBF system, which are the deformation controlled elements and which are the force controlled elements, right? So you understand like the braces that are there, those are the deformation controlled element in your CBF system, whether it will be OCBF or whether it will be SCBF. OCBF means ordinary concentrically braced frames or special concentrically braced frames, irrespective of the system. The braces are the fuses in the system, which is a deformation controlled element, and the beams and columns are the force controlled elements, which means the nonlinearity has to come in the braces, which will act like a fuse in the system and protect my beams and columns. Now you can see the hysteresis behavior or the nonlinear behavior or the load deformation curve of the braces that is given here. This curve that you see on the right is not for the entire frame, but is only for the braces. Now you understand that normally when we do steel design, we try to avoid buckling in a member. But if you think of a brace element, the brace element, when it is like when the earthquake is coming from this particular side, from left to right, this particular two braces will be in compression, right? If the earthquake comes from, or the lateral force comes from right to left, this particular brace will be in tension. So you understand that during an earthquake, the brace will be subjected to both tension and compressive forces. And if it has to dissipate energy in tension, it will yield in tension. And if it has to dissipate energy in compression, since the length is large, like you understand that the bay width of a particular structure is like Last time we talked about for a steel structure 6 to 12 meters, 12 meters and all if we go, and the floor height is 3.6. The length of the brace and the if you design and if you understand, the nonlinearity in compression comes due to buckling of the brace member. So you can see on the right side that above the zero axis, the loads that are in the positive side are all tension. So you can see the brace as elastic it behaves, and then it yields at this particular level. These are different cycles. The loading protocol is such that it undergoes different cycles. So you can see a large area inside the curve in the top tension side. But if you look at the bottom side, you can see first, after it gets loaded in compression, it buckles around at 40.6 kilonewton. And once it buckles, if you look at below zero, you have lesser amount of energy dissipation in the compression side. So you understand from this figure itself that a brace will yield in tension and will buckle in compression in order to dissipate the energy as a fuse element in a CBF system, which means that this particular curve that you see on the right side is asymmetric in nature, right? You don't have equal energy on both the first quadrant as well as the, let's say, the third quadrant. You don't have equal amount of energy getting dissipated. And that is exactly the reason why, if you look at IS 1893, 2016, and if you look at the response reduction factor for SCBF, if you compare it to moment resisting frame and EBF, they are all 5, whereas for EBF system, SCBF system, it is 4.5. So you don't have enough ductility in the system, and since it is asymmetric, and since the energy dissipation is not large enough, this kind of a system does not have enough ductility to claim a larger R value. So that is why it ends up at 4.5, right? So this is one thing, that you need yielding in tension and buckling in compression to dissipate the energy in the brace. But this is the nature of the hysteresis curve. An asymmetric hysteresis curve is what you end up with. So the main objective, the design philosophy when you design an SCBF system, is to ensure that the plastic deformation or the nonlinearity occurs only in the braces, right? You don't want any kind of nonlinearity to happen in your beams and columns as much as possible. We'll come to define the performance limits under DBE and MCE at a later point. But what we majorly want is, if an earthquake happens, the nonlinearity should only focus in the brace elements. So how do we ensure that in the design? Is by selection of the appropriate brace section. Correct slenderness ratio has to be chosen. Compactness criteria, like last time when we talked about, if you look at table 2 of IS 18168, for brace elements, it gives you a particular D by T or B by T ratio, such that premature fracture due to local buckling, initiation of local buckling, can be avoided or can be delayed. Avoided, I removed that sentence. Last time we discussed that this thing can be delayed. Then selection of brace cross-sec configuration is another thing. There is a limit on the type of brace configuration that has to be selected, which is like for special concentrically braced frame, certain configuration can only be used, whereas in ordinary concentrically braced frame or in a low seismic region, additional configurations can be also used. Then why we call special concentrically braced frame is, like we call SMRF in RCC, where we do ductile detailing. For SCBF, we have to do ductile detailing concept also comes in, which gives it the additional, strength and stiffness, so that it can undergo the larger deformation expected in a high seismic region, right? So efficient system characteristics for a SCBF system includes optimal selection of brace members, proper demand to capacity ratio. Balance has to be maintained between different braces, so that you understand that your braced frame system, structural system may be a 4-story high, and you may be giving braces along one particular bay along the whole height of the system. So you have to ensure that when the earthquake comes in, your damage doesn't concentrate at one particular floor. We'll understand later on that. SCBF system, why R value has reduced is because once a brace buckles at a particular floor, the tendency for the damage to get concentrated at that particular floor increases, which means a soft story mechanism kind of forms as a tendency to form more in terms of CBF systems, concentrically braced frame system. Right. So with respect to that, we have to ensure that we design the system in such a way that once the earthquake comes in, there is a distribution of nonlinearity across the height of the braces, along the floor elements, along the floor, across the floors, in the brace frame system, the nonlinearity has to get distributed and not get concentrated at one particular floor. Next is brittle failure of brace frame should be avoided, like weld or base plate connections. I mean, ductile detailing has to be ensured, and diaphragms which transfer the forces. Normally, braces you don't give it in the interior, right? If you give the braces in the interior, it will hinder the functionality of the building. So mostly what we do is we give the braces along the periphery of the building. Like last time we discussed, like moment frames can be given either all moment frames or on the periphery. But in brace frames, generally we give it on the periphery to avoid any kind of hindrance to the functionality or movement of people. So in that cases, we have to ensure that all the diaphragm, the connectors, the horizontal members, the horizontal bracing are strong and stiff enough such that the forces can flow to these brace members efficiently. And next is column splice failure. Failure in base plate should be avoided. So connection should be saved at any cost. Like last time we talked about, the connection should be the strongest in the whole system. Now, just to cut off this thing, what terms will you associate a CBF system, concentrically braced frame system, with? There are options that I have given here. So, I mean, if you think for it for 2 seconds, you can think that, okay, if I give a braced element into a structure, its strength is going to increase, its stiffness is going to increase, and deformation is going to decrease. So the problem that we had with the moment resisting frame, where stiffness is very less and drift controls the design, CBF is bettering that particular system by when you give a lateral element, the stiffness of the system increases, so deflection is not a problem. So strength is what governs a design in a CBF system. Is there any difference in the mechanism of OCBF and SCBF system? Like we discussed, OCBF and SCBF, compare it to OMRF and SMRF, whether you want to compare it with steel or RCC, it does the same. The mechanism remains the same. It is only that we give some additional detailing, special detailing in the system, such that it undergoes more deformation. Uh, I mean, it is generally given in a high seismic region, right? SCBFs are in a high seismic region. So detailing we give it such that the system can undergo more nonlinearity or more nonlinear deformation and appropriate rotation accordingly. Now, target performance of SCBF R is equal to 6. Like in our code, it is 4.5. In American code, R is equal to 6. Which of the statement is correct? Now, this is where I want everyone to read all the four options that is given below, because this is what sets the performance criteria, right? So under DBE, this is not under 18168, but this is the criteria that you have to follow. Like this is taken from the international code, FIMA code, and this defines as when you do a nonlinear or a performance-based design, let's say under DBE, the interstory drift ratio has to be kept below 2.5 percentage, right? And the braces can yield under this 2.5 percentage, but braces can yield and buckle, but should not fracture, which means under DB level, what has to be understood is that, which is the design basis earthquake level, if you do a nonlinear analysis, a time history analysis, the interstory drift ratio has to be less than 2.5 percentage, with maximum nonlinearity in the braces, where the braces would have undergone yielding and buckling, but it should not fracture. If it fractures under DB level itself, then under high seismic, if something like an MC level comes in, the structure will not be able to handle the lateral forces. So under MC, what is the criteria? The drift should be under 5%. So when you do time history analysis with 11 ground motions, and then you find out the interstory drift ratio and average it out, and if the value, I mean, average out the interstory drift ratio for all the floor levels, the value should be less than 5%. The braces may fracture, but if you use the appropriate compactness ratio, it may, I mean, you want the brace to survive as long as possible. Column bottom can yield. I mean, some braces sometimes fracture, but it should not lead to collapse of the structure. The column bottom can also yield, but the structure, I mean, under MC level, what our 1893 proposes is that the structure should not collapse. That is the same thing under this also, but the interstory drift ratio should be less than 5%. And under DB level, beams and columns, what about them? They should remain more or less elastic. I mean, no non-linearity should come in the beam column element. But under MC level, yes, some amount of yielding can come in the members, like at the base of the column, it can come. Now, if you say at the beam ends it should come, then the problem becomes is that it becomes a dual system, right? If you give fixed end conditions to the beam, then it becomes a moment frame with the braces given there. So it becomes a dual system. In that case, yes, I mean, then appropriate R value has to be also chosen. And then after the brace yields and buckles, you can have nonlinear hinges in the beams also. And then it can go to the base of the column. But if it is a purely SCBF system which takes on the lateral forces, then normally what we do is we give pinned ends to the beams such that they don't take part in the lateral force resistance, and only braces come into play. So you are clear, right? What is the target performance? Why the 5% is given under MC level? Why the system is not assessed or not? I mean, what do you say, recommended to go beyond 5% is because even if the brace survives, the connections tend, I mean, between the brace and the gusset plate to beam column connection, those connections are observed to fail after 5%. So you can understand that even if your brace is alive to dissipate the energy, if the connections fail, then there is no point in having a brace which sticks on for a long time, because then there will be, the braces will not take part in the lateral force resisting system, and the beams and columns are not at all designed for lateral forces, so it will come down. So that is why the value of 5% has been given in the code, and this has been observed under experiments also. So let's understand what is the undesirable performance. I mean, what do we not want? I mean, after all, what we have talked for long, what do we not want in a CBF system or an SCBF system is that we don't want connection fracture, right? The one that I talked just now, that if the connection fails, the braces are no longer useful. The column should not buckle. The force controlled element should not undergo any kind of instability. Same goes for the beam. You can see here, this is a kind where the bay is like this, and then a inverted V shaped braces are attached. And you can see at this location, there is like a failure in the beam element. The nonlinearity is concentrated at this location. You will come to, we will discuss this particular aspect later, and this is one of the things where 1994 Northridge earthquake has, or 95 Kobe earthquake has shown this kind of failure. And later on, this has been added into the code as to how to cater for this type of failure, which was not done earlier, right? Then there should not be any column tension failure or splice failure or base may failure. I mean, nothing should happen to the beam or column or the connections. Anything and everything, nonlinearity has to happen in the brace under DB level, and MC level, okay, little bit of yielding in the base of the column has to be. So what is the desired performance? Brace buckling, as I said, instability in the brace in terms of global buckling of brace is allowed for a CBF system. Yielding in tension is allowed. Column flexure, I mean, bending of the column is okay, and beam at the middle is also okay in this particular system, right? So these are the allowable or desired performance in the system. Going across, we are talking, we have not come across the design as such for the time being. We are talking only about the braces right now. Our main hero of the story are the braces. So the critical parameters that we are talking about for the performance of the CBF system as a whole, with respect to the braces, we are talking about the slenderness ratio of the brace. I mean, if you look at, these are all the parameters, critical parameters that affect the performance of the braces, out of which these first three, slenderness ratio, compactness ratio, cross-sectional shapes, are the most important one, are the most consequential. Rest are not at all even, I mean, having a say in this, but the majority or the maximum impact is due to these three. So first is the slenderness ratio. You know that the bay width is fixed in a building, the height of the building is fixed. So you have a particular slenderness ratio that you end up with respect to the configuration that you go, right? We'll come to configuration, but you understand that if I go diagonal from one corner of the bay to the other corner, or if I do an inverted V with the connection coming in the middle, like in the last slide, like this, I can give a braced arrangement like this, or I can give an arrangement from left corner to right corner top. So I can give different combinations. So the slenderness ratio, you have to control. Now, what the code gives is, as per AIC 341, there is an upper limit on the slenderness ratio, right? In our code, this comes about 160, 165, some value is given. So what you have to understand how the slenderness ratio effect is that, if my slenderness ratio is very high, if the brace ka slenderness ratio is very high, which means if I have a fixed length of brace, then the only way by which slenderness ratio can increase is if I decrease the thickness of the element, or if I reduce the size of the element. If I do that, my slenderness ratio for the same length is going to increase, right? Now, yeah, Dr. Narayan, IS 800 section limits as 120. But if you look at section 12 itself of IS 800 2007, you will find the slenderness ratio 165 there. And then in 18168 also, there is a limit that is given there, right? So let's understand why it is given as. Is that you understood, right? If the length of the brace is of a particular length, what you might be reading, Dr. Narayan, is from that normal element, like a column element or a beam element, what is the maximum compression limit and tension limit that is given there. Look at section 12, which is where we need this element to be behaving like an energy dissipating element in earthquake. So there the maximum limit in Indian code is like 165 or 160. Kindly look into the code. In US code, it is given as 200. So what is the case is, if my slenderness ratio increases, my energy dissipation capacity decreases. Now you can understand that where that thought process comes in. My cross section reduces for the same length of brace means my tension capacity of the brace decreases. Also, since the slenderness ratio increases, my compression capacity or the buckling load is going to come down, right? It will be a very low value. So in total, my energy dissipation capacity from a very slender brace is going to be very low, wherein if I keep on increasing my slenderness ratio, it may become like a wire element, right? It will be only a tension element kind of a thing. If my slenderness ratio decreases, right? If my slenderness ratio decreases means for the same length, either I'm increasing the thickness of my element, let's say, that will cause increase in my tension capacity. I mean, yield value, it will also increase, and it will increase my buckling capacity. So the overall area under the hysteresis curve, which is the representation of the energy dissipated during an earthquake, will increase for a low slenderness ratio. So you understand, as the slenderness ratio increases, your energy dissipation capacity decreases. As your slenderness ratio decreases, your energy dissipation capacity increases, right? Keep this in mind, राइट. स्लेंडरनेस इंक्रीज होता जाएगा तो रस्सी जैसा बन जाएगा. So your energy dissipation capacity decreases, whereas if you reduce it, it becomes a very stout section, very strong member, तगड़ा मोटा member रहेगा. So your tension capacity also increases and your compression capacity also increases, eventually increasing or consequently increasing the energy dissipation capacity. Now, in Indian code, there is no lower limit. In American code, there is no lower limit. But in British code or Euro code, there is a lower limit also given for, the braces. Why that is given there? I mean, they have a methodology saying that, okay, you have to limit the lower slenderness ratio to a certain value such that whatever the maximum force that will come from the brace, that will be transferred to the column has to be also limited, column to beam member, like how much amount of force is getting transferred from the deformation control to force controlled element, to limit such that instability, like बहुत ज्यादा load अगर column पे आ गया तो it may globally buckle, such kind of instability might come into the system. So that is why they have a limit, but Indian code doesn't have it. I mean, it's upon design. I mean, you can ensure while the loads, I mean, you are only designing the beams and columns. So you can ensure whether it is undergoing any kind of yielding or buckling or anything. So this is okay. Like an upper limit is necessary, but a lower limit is not necessary. Coming to compactness ratio, yes, last time, like we said, the compactness ratio is to delay the onset of local buckling in the member. So in a brace, global buckling is going to happen because it is the nature of the brace to dissipate energy. Local buckling, if it happens in a very large way due to, let's say, a large diameter, small thickness, then there will be a premature fracture in the braces due to the combined effect of local and global buckling. So that is why table 2 of IS 18168 is where you will find the clause. You will not find it in IS 800 2007. In 18168 table 2, you will find the D by T ratio or B by T ratio for a brace element, where you can choose the compactness ratio, right? The next is cross-sectional shape. Now you can understand that if I give you a choice of what are the, if you go to a metro station or if you go to a, let's say, industrial structure, you might have already seen what type of cross-section that they go. So majority of the places you might have seen a hollow square or a rectangular section. Now, why people go for it is because there is a fixed dimension, the width and the depth. Now, along the width and the depth, what you can do is you can easily locate the center of that particular side, cut a slit inside it, and then inside that slit you can insert the gusset plate. Now that is how the connection is generally made. I mean, we have diagrams coming up where you'll understand what I'm saying. But in that particular case, box sections are much convenient in terms of connections. But the problem box sections have, like hollow square or rectangle, is that they have those corners that comes in. So you can understand that when it undergoes compression, it will buckle globally as well as locally buckle, such that those corners are where the stress concentration will increase. And it has been observed that such kind of hollow square and rectangular sections, due to that stress concentration at the corners, starts to fracture at that location very quickly. So with respect to the cross sections which behave in a best way, I sections are the better cross sections because it's an open flange sections, open sections are there, so there is no stress concentration coming much in an I section kind of a thing. But the problem is the connection becomes a bigger problem in terms of I sections. The second best are hollow circular sections, where the only problem is how to locate center at one end. That is okay. If you cut a slit at one end, let's say everything is well and fine. But when you cut the slit at the other end, if you are using, I mean, no extra gadgets or any laser type of equipment or anything, and you are doing at site, the most probable condition that you would end up with would be an eccentricity in the loading. You may cut slit at one end, but getting an accurate or inline slit at the other end of the brace will become a problem in terms of circular this thing. Yes, if you go for I sections, that is the problem. Lateral torsional buckling will also come in. But yes, you can change the configuration of the braces as that you can end up with having lateral support to the members also. So you can have an X type of a configuration where the braces can be connected at the middle such that it can have some support there. So the lateral torsional buckling in an I section can be avoided. But the major problem, see, design wise, you can play with the cross sections, provide support, etc. But providing an easy connections, I mean, the problem is I section kelly, you can think that okay, if I think of it right now, yes, I can make out a connection right now. But to ensure that okay, if you provide a connection such that you want to get maximum energy dissipation, then the problem is I have to make it buckle along the major axis, right? You can connect it along the minor axis of the I section. It will buckle around the minor axis, but then you don't have enough energy in the compression side. If you can make it buckle along the major axis, you may get a higher capacity than what you get along the minor axis. So such kind of problems happens in an I section, but still it does not undergo very much premature kind of failure as it is observed in hollow, circular, and square. So if wind is governing your design, then it's good to go with square sections, as the braces have to be elastic throughout. But if it is earthquake that is governing in a high seismic region or in a low seismic region, best to go with hollow circular with provided correct. We'll come to knife connections also. You can cut the slit there in a circular section using gadgets are there, laser type gadgets are there. But yes, so preferably go for open sections or circular sections with good connections. Like we talked last time, there is no connection procedure given as such in Indian code. If somebody comes up with a pre-qualified connection or a connection procedure, we have done few works in that particular area. So I'll show you later on how to do the connections, etc., or which reference to look for while doing the connections. Now, loading rate, yes, it has a, I mean, if you ask me, the high loading rate generates high strain rate, which leads to brittle fracture, but it also increases the temperature, which improves the fracture resistance. So, high loading rate has a effect both positive and negative. But what has been observed over from 1970 till now as the loading rate, like the rate that we expect during an earthquake, does not affect the performance of a brace. So during an earthquake, if you do a test, let's say in an experimental lab at very low particular frequency or a certain low rate, certain kilonewton per second or something like that, this is a load that you're applying, it doesn't matter, because loading rate does not have an effect in terms of the performance. Like you will not get a varying answer if you do it at a different rate. Now you can understand, if I fill the ground, if I fill the tube with some concrete, obviously it is like a composite section, so it will have an enhancement. But normally this is not done anywhere. But yes, if you fill the box section with concrete, it will improve its compactness criteria, right? It will, the local slenderness ratio is going to improve, and that will avoid the occurrence of local buckling in the member. but such practices are very rare. Now, loading history, yes, during an earthquake, you might think that the brace might be subjected to tension, compression. But sometimes it may be like if you're in a near field earthquake or a far field kind of a situation, the kind of type of loading, the way in which tension and compression comes as a sequence may be different. Maybe it's only tension dominated, maybe it may be compression dominated, or it may be the kind of increasing amplitude of cyclic tension compression that you normally look at. But that way you have to assess. I mean, it has a different behavior, but it has to be assessed if you have the backbone curve of braces, which you, again, AC 4117 are there. 4117 provides you with the nonlinear property for braces that are there. You can go ahead and do that thing. We have some publications also with respect to the performance of Indian box sections and hollow circular sections. You can also refer them while doing your nonlinear assessment. Now, yes, if you go for lower grade steel, obviously we already know that if we go for a low grade steel, its ductility is going to be better and its fracture life is going to be enhanced. So these are the critical parameters with respect to braces in a braced frame system, which we have to take care such that we get the maximum optimized performance from the braces. Right. So now if we look at a braced frame system like this, like you can see that the base is fixed. The representation may be a little bit odd, but what I meant is, okay, this is a fixed base. This is a pinned section here. This is a pinned section here. So majority of the lateral forces will be taken up by my brace system. Now, if you're doing this analysis, let's say performance-based analysis or a nonlinear analysis, you need to understand the first thing is to identify that where, what type of a hinges will form in the system such that I don't miss any nonlinear kind of performance in the system. And the second is where to apply. I mean, what would be the location? So if I look at an ideal performance from the system, then the first plastic hinge are required to form in the braces, and that too at the middle of the braces. It's the same concept like in a Coupon test, why the yielding starts at the middle of the specimen. The same happens with a particular brace, that okay, whether it is tension, compression, it is easy to understand that that is a location where the buckling, the maximum deformation in the buckling deform shape is going to happen. So the plastic hinges, you have to assign it at the middle of the braces. The second is at the gusset ends. So you can see here that's the gusset plate there, but normally what we do is you can understand that the gusset plate is moving out of plane, right? When the brace is going to buckle, the gussets are very thin plate elements. So it's like if you think 80 brace element, the gusset plate might be 3 to 6 kind of a thickness. So you can understand that the outer plane stiffness of the gusset plates will be very low. So normally हम model करते time, what we do when we model the brace elements, what we do is we give a moment release for the brace element because we don't consider the contribution of the gusset plate in terms of providing any moment restraint to be very negligible. That is why, I mean, the contribution is very less. So that's why moment release is good enough rather than giving a hinge there. Next, ideally, it will form at the base of the column, right? And then it may also form at the middle of the beam here, right? Earlier, as I told you, I mean, I can explain it to you right now here is, you understand that during the earthquake, why the hinges are getting formed here is, for one case, you can understand, okay, for the beam mechanism to be complete, already pinned connections are there. So the middle may form hona hai. Now, why is this critical? Or you remember the undesirable may, one location was shown where the middle of the beam got failed. That is because if earthquakes come from left to right, this particular brace is in tension. I repeat, if the earthquake comes from left to right, this particular brace is in tension and this particular brace is in compression, right? Everything is well and fine. But once, let's say, the right side brace, if the load increases, the right side brace will buckle, right? Once it buckles, you understand that on the very initial slide, what I showed as the hysteresis curve, that once the load, I mean, when the brace buckles, then it does not have enough compression capacity on the second round. So if the load was 40 kilonewton on the compression in the first cycle, next time when it comes, it will be less than how much amount of compression it will take, 20. Then it will keep on decreasing. So if you look at the location, this location, if I draw a tension force here as the peak value, compression force in a post buckle regime, it may be a lower value. So if I resolve the forces here, you'll find that there will be an unbalanced vertical force and a horizontal force that is going to come here. So in a pre-buckle to post-buckle, pre-buckling is where this brace yields in tension and this brace undergoes buckling to a point where this brace is still yielded under tension, but this is reached a post-buckle domain where the compression capacity are reduced too much. Then there is an increase in the vertical as well as horizontal forces in the members. That will cause the hinges can easily form at this location if you don't design the beams for these. So this particular arrangement, the inverted V or chevron is the name that is given for this configuration. उसमें आपको specifically याद रखना है कि the beam has to be designed for the additional forces that comes due to the post buckled condition of the braces, right? So if you design such a beam, the beam sizes will be very large for a chevron kind of a condition. You'll ask, अरे beam का size बढ़ गया तो मेरा column का size बढ़ेगा. So the question comes is, okay, strong column, weak beam criteria that need not be satisfied because the ends of the beams are pinned, right? So if it is fixed and you have a chevron arrangement, then the problem is going to be increased, right? If I give a fixed condition as a dual system and I depend upon my braces to be then also the kind of hero in the system apart from the beam hinge forming here, the beam unbalanced forces are going to develop. The fixed end problem के लिए आ जाएगा कि strong column weak beam has to be catered for. So then that will result in giving a higher column section. So you understand where and all the hinges are getting formed. What type of a hinge will form here? It is an axial hinge. See, I give a moment release here. If I apply any lateral force, it only axial force gets developed in my braces, right? That's why we initially said that the CBF system acts like a vertical truss system. So only primarily axial forces are there in the brace frame. So axial hinge will form here. Moment release I give at the brace ends. This is a PM interaction hinge that you normally give because moment as well as axial force govern. And this will be a moment hinge that will form at the middle of the beam, right? Can we use brace system in an RCC building? Yes, we can do that. I mean, it is just as the same case system like shear walls, right? Shear walls are also there to give you additional strength and stiffness to the system. But shear wall problem ये करता है कि it increases the inertia of the system. So what you have to take care is, the question is, can you give braces, steel braces in an RCC system? I have an image at the very end where we have done some tests with respect to that. So the two things is, the concept remains the same. The beams and RCC beams and columns have to be capacity designed for the forces that will come from maximum forces that will come from the braces. That has to be designed in such a way that under DB and MC level, whatever we talked about, कि भाई purely elastic होना चाहिए under DBE, MCE में चलो RCC होगा तो it becomes a dual system. I mean rigid connection है. I mean with respect to the detailing, if you can give a rigid connection, but you have to think about the anchor forces. Like the main problem comes is the connection between the steel brace and the RCC element. So if you can cater for, I mean, there are many options that are available right now, that if you're casting the fresh concrete, things can be embedded inside, which will give better performance. But even for retrofitting of an RCC, old RCC building, post-installed chemical anchors, like things are already available by different companies, which can be also used. So yes, it can be used there, right? So you have understood what type of hinges can form, where it will form. If you model it, what and all care you should take, you understand right now, right? This is the general, that hysteresis curve that you saw at the beginning. This is what I was explaining, that okay, if your slenderness ratio is very high, then after A there will be no plateau between A to B. It will dip like anything, like a pointed end it will go if your slenderness ratio is high. So this is like, okay, this is a low slenderness ratio brace, which after buckling will go here. I mean load drop will be there. If I unload it from there, there is this, I mean zero it will go, then I take it into tension, then it will yield in tension. And one good thing with steel is that you might see the hysteresis curve of RCC and all, the pinching due to concrete getting damaged or cracked, pinching comes in, which means you have a shrinking at this particular level between the curves here. But in steel that doesn't happen. So steel structures are better at energy dissipation than an RCC structure, right? So this shows the hysteresis curve of that particular level. So the point is, okay, for the cycle, if the brace buckles at a point A, let's say 40 kilonewton, when it undergoes the second cycle, it approaches a value lower than that 40 kilonewton. And after multiple cycles, it stabilizes. So normally क्या बोलता है कि the code if you can write your questions in a very short manner, na, I can able to read and answer. Sometimes the questions are very large that when it pops up on the right side, I'm not able to read it, right? So my answer is the brace after it buckles, it doesn't fail. You have to understand one thing that any material, regardless whether it is concrete or steel, RCC के बारे में भी ये सही है और steel plate या किसी member के बारे में, that an element fails only in tension. It fractures in only in tension. Buckling की वजह से the only problem that you're having is there is a load drop that is going to come. It is going to buckle at a certain. I mean, you already understand the Euler buckling theory, etc. for elastic buckling, right? So after a particular load it applies, it buckles from there. So if this happens in the second cycle, it is not failure of the element, it is just buckling of the element, where the buckling capacity or the buckling load keeps on decreasing under multiple cycles, right? So it happens that in Indian code, this gives like for the pre-buckle, like when the buckling load is let's say 40 kilonewton, the post-buckled case, what the final value is going to be. Let me come back to this. It will be easier to explain from here. If you can see here, this is the first instance of buckling in the member. You can see it gives a certain value and it stabilizes to a particular number, right? It still is dissipating energy in compression cycle, but the post buckle value may be 0.2 times the peak compression value or 0.3 times. So our code takes a certain case. 18168 considers ki okay, if C is the maximum compression force in the braces, after it buckles, the post buckle analysis के लिए it is dropping down gradually. So it is not like कि एकदम से 0.2 maximum C max या 0.2 C max नहीं हो रहा है. It is gradually dropping to reach a value of 0.2 or 0.3 C max, right? So our code takes 0.2 C max as the value. American goes for 0.3 C max के case का value. Like there is a buckled load, there is a post buckled value that it reaches, gradually dropping down from value. Let's say this is 40, this is let's say 30, this is 20, then 20 15 उस रेंज में आ जाता है. तो उसके वैसा ये है कि the peak load in compression after many cycles stabilizes and drops to a value of an average value of 0.2 Cmax or 0.3 Cmax. Our code goes for 0.2, American code goes for 0.3. So that is what we consider as with the maximum capacity in compression after multiple cycles. So likewise, this value after multiple cycles gets stabilized, but it never drops to zero. So the member failure का नाम से सोचा जाए तो yes, buckling is a type of failure, but still it's able to dissipate some amount of energy, a very minimal amount of energy, right? Buckling strength, A.K. Jain sir found 55% in most experiments, but if you look at literature, Dr. Narayan, you will find that 55 is a very high value. So you have to understand that, let's say our drift under MC level is 5%. Calculate in that way, 5% के लिए maximum axial deformation in the brace would be how much? If you do n number of cycles, yes, the braces come under ultra low cycle fatigue case, where under earthquake only 20 cycles or 30 cycles are what the brace are going to undergo. In that particular number of cycles, how much is the drop of compressive strength? You look at literature, and I have experiment results also with me. So you will find that whatever they said is true. That, and one more thing, if you take 0.55 of Cmax and if you find out the unbalanced force in the beam, right, you will get a lower vertical force that will come in the beam. But if you go for a T max and 0.2 C max as the value at the center of the brace, like let's say this is T max and 0.55 C max ke against T max and 0.2 C max ke against, which will yield maximum forces, vertical forces in the member, means it is a lower value. So different tests, I mean, you may say one particular test में 0.5 तक गया, it may be a brace of lower slenderness ratio, but the code cannot give too much variation in its design. So maybe, I'm not claiming that it is wrong, but you can see here also, this is one more hysteresis curve where, let's say this is a beginning, this is the elastic cycle where everything is okay, there is no energy dissipation in the elastic cycle. And when the deformation increases, the first event to occur is the global buckling in the member, which occurs, like you have to understand event wise that it occurs at around 0.3% interstory drift होते ही buckle हो जाता है, right? You have to understand कि 5% drift, lateral drift is what are maximum drift criteria that we expect before the connection fails, where we don't want entire collapse of the structure also to happen, where we want maximum braces in the system to have undergone yielding and buckling, and minimum amount of energy dissipation has happened. But looking at that, the event of local buckling visibly actually occurs around this 0.3% के around हो जाता है. Then comes the local buckling, which happens at a later event. मतलब even if the section is like of, let's say, a higher D by T ratio or higher B by T, the compactness ratio is not good but very bad. But then also what happens is global buckling पहले होता है, बाद में due to different cyclic, you can understand, if you take a tube, you bend it backward and forward, the local buckling event occurs at a very later point. But the issue is once the local buckling occurs, then it's like global and local का effect दोनों मिलके, then the fracture initiation starts very quickly, right? And once the fracture initiation starts, then you can understand that this cycle में fracture initiation यहाँ start हुआ, then the brace does not have enough life left. So, so you have to understand that global buckling occurs very early in a brace case. So earthquake जब होता है तो आप देख पाएंगे, अगर visibly आप किसी structure के बाहर ऐसे खड़े हैं, तो you will find out the global buckling to occur in the brace element. And if it is out of plane हो रहा होगा तो वो लगभग 200 to 300 बाहर की तरफ आएगा. So if there is a glass facade, it is going to damage that. If there is a masonry or something like that as a cladding element कुछ दिया होगा, तो it is going to damage unless so much amount of gap is to be given. But एक बार local buckling हो जाता है, तो then the event starts to happen very quickly. That fracture initiation also starts. You can see earlier, this is a box section, right? Hollow square section है. इसलिए you can see at those corners itself are the location where the fracture initiation starts, like the point that I was mentioning earlier as the stress concentration, and then the final fracture occurs at this location. So what you want is कि यहाँ पे भी आप देख सकता है कि ये brace is not a good brace, such that वो जो drift satisfy कर पा रहा है वो nearly 3% ही satisfy कर पा रहा है. So whatever IS 18168 is, table 2 is, it is truly inspired from 34116 का table D.1, which is related to highly ductile members के लिए जो value दिया है वही उधर डाला हुआ है, totally inspired from 34116, which is like a stringent way to say that if you use that compactness criteria, then at least the brace will survive till 5%. That is the case. But आप देखेगा कि 2005 का ये ऐसी कोड, then I think 2010 में था, then 16 में था. You will find out that every now and then the code is getting revised. ये वाला जो compactness criteria that has become more and more stringent. Like वो ratio is dropping such that you pick up a lower value such that the brace achieves a higher capacity, which means you can understand 1970s tests are being done continuously. So as and when more detail is available about a particular cross section, steel is very costly to do tests in. So you can understand how much amount of tests are being done. So some are simulations, some are tests. So based on every result that is being published, उस basis में code is getting updated again and again. So yes, we have already talked about slenderness ratio and compactness ratio. This is what is given in 34116, which would be similar to what we have in IS 18168, right? Why do you think there is a limit on slenderness ratio? Out of the options, just take 2 seconds to read. Sorry. To avoid damage of the cladding and connection, maybe, but even for a low slenderness ratio to undergo lateral deformation of 5%, then also the member undergoes 200 So that is not the main thing. To avoid tension only braces is the answer. Rest are, I mean, when the slides come to you, you can go through it and think on it more, right? The next question is which all options can you associate with brace of low slenderness ratio? I'll move it slowly. I'll read it and you think what are the things that you can associate with brace of low slenderness ratio, right? A brace of low slenderness ratio is the one which dissipates more energy. Yeah, one more thing I left out is even though braces of low slenderness ratio dissipates higher energy, it is prone more to fracture, early fracture than a low slender. So if you have a very slender brace, yes, it dissipates very low energy, but it has a higher fracture toughness than what you have for a low slenderness ratio. So that is why in your structure, if you end up with a brace of low slenderness ratio, you have to ensure that you comply with the compactness criteria. Otherwise, your brace is anyway going to fracture. So that I missed out in saying that key low slenderness ratio, even though it is good, has to meet the stringent criteria of compactness criteria. Otherwise, it is more prone to early fracture than of a brace of a higher slenderness ratio. So yes, a brace with a low slenderness ratio is related to high energy dissipation capacity. Premature fracture of brace with high compactness ratio, correct. With low compactness ratio की case में नहीं, because low means it is stringent, the thickness is very high. Low energy dissipation capacity is also not the answer. Good choice in chevron type configuration. No, because the values are very high. So tension values are high, compression values will get very low, which means unbalanced forces in the beams will be very high for a low slenderness ratio braces, right? So when we design, let's say a brace, I mean, just to give all engineers here a kind of idea, if you go upon designing a low to mid-rise structures, let's say 3-story to 12-story structures आप design करके उसमें आप brace अगर डालेंगे, तो slenderness normally varies from 40 to 100, and it can be 120 also, right? So when are we using can you write that question again? When are we using some term that popped up and went away? So if you can write that question once again, maybe I can talk on it. In buildings generally, so what I was saying is, even if there is an upper limit of slenderness ratio, if you are designing a low to mid-rise structure, what the problem is, the slenderness ratio is going to come in a particular range only, because it is a fixed length that you have. The demand is also going to come, strength is going to govern the criteria. So when you end up with the design, the slenderness ratio normally varies from 40 to 120 or 100 उस case में, right? And next question is, this is just a recap of whatever we have done. If concentration of strains initiates fracture in braces, which shape of brace would be ideal? Now you'd be very clear that, okay, I sections are better. Second is hollow circular sections. Third, if you are in a low seismic region or if wind is governing, box sections are much preferred, right? Now here is one sentence, one tip, that I section provides 25% larger inelastic story drift and rectangular HSS prior to brace fracture if all factors remain the same. But yes, connection is a problem for I section, right? So here are some numerical simulations just to show you one more time that if I choose a particular slenderness ratio, very low slenderness ratio, I said our slenderness ratio in a structure varies from 40 to 120. If I'm going for a very low slenderness ratio and I vary my D by T ratio 10 to 30, 30 is beyond the code limit currently. You can see the black color failing at a delta by delta Y of 5. Around at that value, it is getting fractured. But if I go for a red color D by T, a stringent value of compactness ratio, then I'm achieving a larger deformation. If you go the highest spectrum of slenderness ratio, let's say American code के हिसाब से, you can see what is the issue, that it becomes mostly like a tension member only. You have nothing at the bottom level. So you understand, if you're giving a braced system, braces in a system, it cannot be just one single brace in one floor. If you're giving a brace, it has to be a mirror opposite, has to be also provided there. So two braces have to be provided, because if the earthquake comes from one direction, one will be in tension and one will be in compression. If it comes in the opposite direction, the earthquake, the other one will be in tension and first one will be under compression. So you cannot give only a single brace, because single brace diya to, if earthquake happens in a cyclic way, I mean, it laterally deform karta hai, तो then the problem comes is ki, okay, then the problem comes is ki, what I was saying, that then the problem comes is ki it will have no capacity. Compression mein buckle kar gaya to all the lateral force demand will go to the beams and columns, right? So that you don't want. So that is why slenderness ratio बढ़ जाता है, तो there is a problem that compression में energy dissipation becomes very low. It becomes like a rope. So if I calculate the area under the curve, area under the hysteresis curve in the last slide, then you can see that if my D by T ratio is 10, so then each cycle that I'm going, I'm achieving a higher energy dissipation. Whereas the black color, which is of a D by T of 30, it is failing very early. But if I go for a larger slenderness ratio, then even I mean, that is the point there is ki nothing is happening. I mean, no dip is there, which means a higher slenderness ratio has a lower energy dissipation capacity, right? but it has lesser tendency to fracture early. So that is why look at the black one is flat, rest everything is peaking. Whereas if you look at a lower slenderness ratio, only the red one is peaking till the end. Till the end, 0.025 axial strain corresponds to 5% interstory drift. Rest everything is dropping down. So once again, just to clarify or just to kind of recapitulate, in which case would we use buckling restraint by conventional braces good or BRB? Okay. Let me just recapitulate and then I'll answer your question. It is that if I have a slenderness ratio in the brace to be lower, it dissipates higher amount of energy, but it has a tendency to fracture early unless you control the D by T ratio accurately. I mean, more stringently. That is why if you control here, it is getting positive till the end, but rest all are failing. If your slenderness ratio is very high, if lambda is 200 here, your energy dissipation capacity is much lower. You can see here the energy dissipation is 800 kilonewton meter, but here it's only 30, 40. It's very low, but then your fracture tendency becomes very lower. So the braces survive till 5% drift तक तो आराम से survive कर रहा है, even if it goes beyond the D by T ratio limit mentioned by the code. But no use. What is the use if you give a brace of very high slenderness ratio which cannot take up energy? So we have done some test on Indian steel structures and we have given what should be the minimum slenderness ratio such that you can achieve a certain level of drift level karke. We have given a particular kind of for Indian sections only, right? So we have done some testing. So you can see here in this particular test that the arrangement is in such a way that earlier Dr. Narayan was saying about some knife plate. Um, with respect to which I mean this is the gusset plate, let's say, but there is a knife plate also given, as that the nonlinearity happens in this particular area and it undergoes in plane buckling. Now coming back to the question, I remember right now many questions are coming. I only remember that BRB kind of question. Buckling restraint braces are much better than CBF systems because they are meant not to buckle. I mean, they give equal energy dissipation in tension and compression cycle. So whatever value, I mean, the brace is this brace. There is a core element, but in a buckling restraint braces, what we do is we encase the inner core element. Let's say this is a brace here, which is buckling globally, right? If I give a protective coating or a shield around it, such that the buckling of the member is kind of, I mean, I'll tell you the concept behind it. Is not happening. Then what? Let's say the buckling, there is a shield that is given around the brace, such that the buckling is stopped. Then what happens is you have equal value, whatever it yields in tension, the same value you will achieve in compression also. So there is equal energy dissipation, tension, compression. How does it reach out? Stop किया तो buckling stop किया तो yielding in compression कैसे होता है? It's not directly the same, but if you remember Euler buckling theory, you understand that the Euler buckling equation for critical buckling load is pi square EI by L square, right? But you understand that there is an n square also coming there, n square pi square EI by L square, which normally n becomes 1 as the first mode is what is governing the buckling. It's a least energy वाला है तो सबसे पहले वही होना है करके we normally give as n is equal to 1. But when we if I give a strong casing around it, normally concrete ka casing diya jata hai, yeah, you can give an all steel also. If I stop the first, if the distance between the brace and the casing is such that it is very low, that as soon as it touches the casing, it the first mode gets stopped and it goes into the second mode. And if the gap between the restrainer and the core element is such that you can make it into go into higher modes of buckling, then n square pi square बढ़ता जाएगा and the peak value that it can achieve is the yielding in compression value. So BRB at any time, if you look at the R value also, BRB is a better system than CBF. But since our code currently does not have it, but in future surely BRBF systems are going to come in the code also. So in that case, you should go for a BRB system. In which case, one good thing is there is no need for any mirror brother to form. Like in a CBF system, agar maine ek brace diya, I have to give another brace here as a mirror opposite. If it is a BRB system, it can be a single system as a total, right? उस केस में, but there is a problem. Every good thing has some good or minus, plus minus रहता है. BRB के system में, like you can understand. Once I'll come to design, I'll talk about that particular aspect also. Send a question when we start looking at the design aspect, right? Us case mein you have to understand how the design of CBF is done and what governs the design in BRBF. then you will be able to understand the negative part of the BRBF also. So when we reach the design part, when I said we are beginning the design, you remind is a brace of 88.9 external diameter to 3.2. You can see that visibly, you can see the global buckling in the member. Then local buckling is looking like this. I mean, this is strain gauges being stuck around it. So visible, thoda sa clarity kam hai. This is string pot that is there to measure the lateral deformation that is there. This you can see a small bend in the member. So उसी को ही local buckling हम कहते हैं. Then fracture initiation, you can see at this particular right above the cursor location, you can see that there is a crack visible. That is the initiation of the fracture. So a hollow circular is better than a hollow rectangular kind of a section or a square section. Fracture evolution and finally the fracture. So after fracture initiation happens, as I said, the total fracture happens very quickly. This is the fracture. Now, if you look at a, a brace section, this is a hollow square section 49.5 by 49.5. उसमें आप देख सकता है कि the local buckling is looking like this, and then where is the fracture initiating? It is initiating at the corner, right? And then the final fracture is happening. So that is what is explained earlier, that high stress concentration occurs at the corner, and hollow square or rectangular sections are not good for a seismic thing. Now, this is the outer plane buckling. Don't look at this is a test setup. This is not a real structure, but yes, gusset plate is there. This is the gusset plate there, and it is undergoing outer plane buckling that is happening there. And इसका जो outer plane stiffness of this gusset plate is very less. So अगर मॉडल कर रहा है तो गजट प्लेट को मोमेंट रिलीज कर सकता है, राइट? नाउ हियर इज दैट नाइफ प्लेट कॉन्सेप्ट, दैट मेरा क्लैडिंग है या ग्लास फसाड है and the brace is buckling, and it, as I said, it undergoes outer plane deformation of 200 to 300 mm, let's say. So usse mera facade, my facade and cladding elements may get damaged. So better way to do it is by allowing in plane buckling of the braces. So you can see that there is an end gusset plate, and then there is a knife plate which is there. In the knife plate there is a slit cut which gets inserted inside uh, this particular location, and then the braces are there over which, I mean, you can see that right now what I made is this particular plate is much thicker, and this is a thinner plate, where I ensure that the yielding happens at this particular location such that my in plane buckling of the member occurs. Now, another important part that you have to understand while detailing is, you can see that above the brace there is a reinforcement plate that is given there, right? You can see reinforcement plate that is there. Now you have to understand one thing, that when I'm cutting, slitting the brace and I'm inserting it inside the knife plate, the point, like even if I go with high precision, or as we do in India, we do it with a cutter, with a labor doing it rather than a robotic cutting or anything like that, there will be a small gap that will be formed between the slit and the knife plate, a small gap itself. So to avoid net section failure at this particular region, I have to put this particular cover plate or a reinforcement plate is required. So to avoid net section failure, reinforcement plate is also an element in the design of the, or a detailing of the brace sections. So if I look at the total SCBF system before going, I think after this we are going into the design part. So if I'm going into an order of events in terms of ideal SCBF systems, what I prefer from my system is, first you have to identify what are the brittle failure nature that you don't want in the system, and then what are the good things, or what do you actually need from the system, you have to identify. So once you get this particular slide, I urge every one of you to kind of count in terms of what you want and what you don't want. And after that, what you want may, I mean, in terms of what you want, okay, I've got a, I mean, okay, I'll use English only in terms of speaking. Hindi, I'll avoid. Sorry for that. What I urge you is, in terms of these events that I've shown here, first identify what are the events that you don't want in your SCBF system and what are the events that you want in your SCBF system. Once you have identified what you want, what you have got to do is you have to arrange them in a sequential order as to what event you want to happen first. So you can easily understand that yielding of brace is required. Buckling of brace is then to be happening. Then bending of the gusset plate has to happen. So some amount of yielding has to happen in that particular I'll explain. Rena. I'll come to see. What I want to urge everyone here is design is easy, modeling is easy, analysis is easy. It is about to understand the system that you will understand where you want to give the nonlinear property, how do you want to give the property, that assessment of what are the forces for which you have to design the members. If you go wrong on the analysis part, you will go wrong on the design and assessment part also. So I'll tell you how to do it, but you have to. I mean, BRB may be a whole different topic as such. I understand that. I'll give you more ideas on it. I mean, how can we take this thing forward, etc. But right now, I'm saying understand the sequence of what you want, and then you will understand the system better. So now let's come to design part. Here, I'll make sure that I talk about little bit about how the BRB or the negative part of BRB we'll talk about. So the first thing is we are coming to the how to do the design. This is a little bit tricky, but not so difficult as such. That is there. So in a brace frame design, first you determine the location of the braces, right? So as we said, if there is a problem with my functionality or the movement inside the, I mean, with respect to the movement of vehicles or people, normally what I do is I give the braces along the periphery. One good thing is my torsional rigidity of the building is going to increase if I uh, give my stiffer members towards the periphery, right? So it gives me benefit in both ways. In terms of functionality of the building, it improves the functionality if I give the braces along the periphery. It also improves the torsional rigidity of my system as well, right? Next is determine the configuration of the braces, right? So we'll talk about chevron. I already talked to you about it. Is the inverted V configuration. Single story X is if I have a bay, one X goes like this and the other X, other brace member goes like this, making an X in the system. So this is single story X. And split X is I have two floors from the top left to bottom and from top right to bottom. If I put, I mean, I have a separate images for it. So why this has been given here is because in a high seismic region, there are only a certain type of configuration that is allowed. In case of low seismic region, you have certain additional configurations also that are allowed. So you have to be very careful. So I have listed only the configurations which are related to high seismic region. Chevron or inverted V or V can be used. Single story X and split X are the only ones which are recommended for a high seismic region, right? Next is selection of your analysis procedure. Yes, you might go for an equivalent lateral force method as per your IS 1893K. I have mentioned all the three methods that are mentioned in my IS 1893. So what you will do is you will do your analysis as per 1893, and then you will determine your base shear and story forces, right? You will determine Z, I mean, Z by 2, I by R, SA by G. You'll do all the analysis or response spectrum method you will choose, and you'll find out the base shear or story forces. Once you have determined your base shear and story forces, you'll distribute that base shear into story forces, and then you'll find out the forces in the brace member, right? You will use the load combination that is given in IS 1893 or IS 800. And with respect to that combo, which is like 1.5 dead load plus 1.5 live load plus 1.5 earthquake load, let's say for that combination, you'll find out what are the forces in the braces, right? So the first element, remember, as per capacity design method, we are attacking or designing the capacity deformation control element first, which are the braces. So we'll design the braces first based on, we can know how much energy. Oh, the question has gone. Keep it short, guys, that if you want me to answer, I can answer it quickly, but keep it very short. We'll answer every question at the very end, the long ones. But if you have a question in between, keep it very short so that I can read and answer. You can know how much energy a brace is dissipating in building. Suppose in a building 50 braces, so I want to know. Yes, I'll come to that. It's a difficult question as to how much 50 braces is going to dissipate, but understand the design procedure and then let's look at the analysis also. I have some results of time history also here. So let's understand. So we have determined the base shear, then the story forces we'll find out. With respect to the story forces, we'll use the load combination given in either 1893 or 800. The basic seismic load combination we'll use, and we'll find out the forces in the braces. At a particular floor, you know that you'll have two braces, let's say. One will be in tension and one will be in compression. You know, I mean, you have to fundamentally understand that if you have one brace in tension and one brace in compression for a CBF system, which is going to govern the design? Is the tension going to govern the design or compression? Mostly 99% cases in a CBF system, it is a compression which governs the design for a CBF system. Once you give the brace with respect to the compression capacity, tension capacity of that brace is obviously more than what is required. So you will design the braces first. Then you will check for, let's say, compactness criteria or slenderness criteria. You've understood, right? Let the slenderness ratio be less than 200 as per American code or 165 as per our code. And you will check the D by T ratio as per table 2 or table D 1.1 of 341.16. And you will ensure that this is the final size of my brace, right? Once you have determined the basic size of the brace, you will never again touch or change the size of the brace again, regardless of what the next procedures are going to be. The next procedure obviously is going to be the capacity design of the force controlled element, which are the beams and columns. So while doing that, you will never go back and redesign your braces. I hope that is clear. So you'll use basic seismic load combinations to design the deformation controlled element, that is the brace. Once the brace cross section is obtained, you will use the compactness criteria and slenderness criteria to check if the brace section is enough or not. Once that is done, the brace section sizes are freezed. It will not change later. Now, as per capacity design principle, what you will do is you will use what is the maximum tension force or the maximum compression force that I can expect from my brace that can come to the beam and column. I will assess that particular force and I'll design the beam columns appropriately. When you do design, yes, you're going back to your limit state method and you're designing your brace also, you're designing as per limit state method. Beam and columns are also you're designing as per limit state method. Once you have done the design of beams and columns, if there is any compactness criteria or slenderness criteria that you check normally, do that and that will be the final, right? Now, just to give a closer idea with respect to code, how the code says is it's not as easy as what I have said right now. The first part is clear, right? First part is, let's say you do an equivalent. I mean, just to give you an elaborate attention in terms of how the design goes. Let's say you have a 3-story structure. Rest of the structure is there. You have a braced bay that is there. So you have normally what we give is we give braces along one bay along the height of the building, right? You can go staggered way also, but preferably what we do is we do this way. Let's say you have given braces along this way and you apply lateral forces at different levels. Is braces give nonlinear hysteretic damping? Yes. So what happens is when some brace member goes into nonlinearity or uh, tension compression forces may it is yielding, then obviously it is going to increase the damping in your system. So normally when we design the system for 5% inherent damping, but when brace member undergoes inelastic yielding and compression buckling, the damping ratio might increase to 20 to 30%, right? So that decreases the vibration in the system. Now, without any disturbance, let me finish this particular part, which is important. So we have a building in which braces are there. Lateral forces are applied in this particular direction, and you have one set of brace in tension and the other brace in compression. So the green ones are in tension and the red ones are in compression. So right. So calculate the story forces. You will be either using equilateral force method or most possibly in a response spectrum method in a high seismic region. You will be going for response spectrum method as the base minimum. Then you will calculate the demand as per conventional load combination, which is like 1.5 dead load plus 1.5 live load plus 1.5 earthquake load. You will find out the forces in the members, right? Okay. Combination might be, there are different combination. I'm just talking about the basic combination that is given normally, right? Once that is done, once that particular values are done, you will get some tension values in this member, one compression members value in this. You will get tension, compression, tension, compression. What I said is predominantly the compression value is what governs the design of the braces, right? So once you have designed the cross section of the braces, you will check, okay, whether that particular brace is satisfying the tension capacity, and most possibly that is going to pass in terms of tension check also. Then once that is done, you will check the compactness criteria as well as slenderness criteria of the braces, which is like, okay, whether it is satisfying that particular criteria, then completely done. My braces are completely finalized and I'll not touch it further. Now, for the capacity design of the force controlled element, there are two methods. One is the global analysis method and one is the local analysis method, right? The complication is not there in the design of braces. The complication is with respect to the additional steps I have is with respect to design of the beams and columns, right? The global analysis method ke liye, what you have to look at is IS 18168 gives you, as per clause number 5, read this design earthquake load shall be estimated and combined as per 1893 along those in table 4 of 800. In addition, the following combination shall be considered for design of columns of SMRF, SCBF, EBF, beams in SCBF, EBF, braces in EBF, and all connections which are part of structural system in steel building. So this particular sentence, if you read it carefully, it points only towards the force controlled elements in different systems. So it points about columns in moment frame, columns in SMRF. It columns of SCBF is also force controlled, EBF is also force controlled. Beams in SCBF, it is missing the MRF because MRF mein beams are deformation controlled elements. So beams in SCBF and EBF are force controlled element, and braces in EBF, I mean, contrary to what is there for CBF, braces in EBF are force controlled element there because link element are the deformation controlled elements. So for all these member design, it gives you a combo 1.2 dead load plus gamma LL live load, I mean live load factor, whatever is given by the code, plus 1 times ELM. Now, if you look at 1 times ELM means omega times earthquake load, right? Omega is the overstrength factor, which is 2.5 for SCBF and 3 for SMR. 3 for, 2.5 for SCBF and EBF and 3 for SMR. So what you will do is you will take your same model of with the braces, and you will use this particular combo with the overstrength factor and find out what are the forces in the beams and columns. And when you do design, let's say as per ETABS or STAD element, if you do the design, you will obviously find that once you've already designed, let's say for 1.5 earthquake load, if you've already designed the braces and the factor is 2.5 here, the braces will be red in color, showing that the demand is more than the capacity. But as I said, your vision or your, focus should be for the design of these blue elements only. Even if the brace fails, the analysis results with respect to what is the bending moment, shear force, or axial force, you are looking only at the design of beams and columns. You are not looking whether the brace has failed or not. So you will use this particular amplified earthquake kind of combination or the overstrength factor included combination for designing the beams and columns. So you will end up with one size of beams and columns. That is whole what is the global analysis. Now the next is the local analysis. This is where a designer or a researcher, what he has to do is he has to remove the braces. He has to, let's say, save the file, make it as a different name as pre and post buckled analysis, some name he has to give. And in this, what we are trying to think of is let's say I have a brace, I have finalized a brace size. And if I remove the braces from the structural system, and then I give the components of forces there, T max, which is I take two conditions, let's say pre-buckle condition and there is a post-buckle condition. In pre-buckle condition, I consider that all my floor levels, that is where it becomes a little bit complicated, that even if it is a 3-story structure or even if it is a 12 or a 15-story structure, we are taking a huge consideration that all the braces at all floor levels which will reach their Tmax and Cmax simultaneously. And under that condition, if you remove the braces and if you give components of forces like this T and Cmax and resolve them at these locations, at these nodes, and find out what are the forces in my beams and columns and designed accordingly, then that becomes the pre-buckle condition, right? So the intention is this particular clause came in after 1994 Northridge earthquake, after realizing that once the brace buckles, it may be giving unbalanced forces to the beam, leading to the failure of the beam. So this particular clause was not there before that failure was observed. But once they realized that, okay, if I do only the global analysis and forget about what happens once the buckling initiates in the system and the brace reaches its lowest compression capacity of zero 0.2 Cmax as per Indian code and 0.3 Cmax as per American code, there is a condition that the beams may get damaged if I don't cater to that particular clause or condition. So that's why they introduce this local analysis. So in this local analysis, you understand that we are mimicking the effect of if lateral forces are in the system, what is the tension and compression that is coming in the brace member. So this Tmax and Cmaxes, my brace, whatever I have designed, what is the maximum tension force it can give, what is the maximum compression force it can give, you have to consider that. So no lateral force will be there. You are giving the effect of that lateral force inside giving this particular look. So lateral force aata hai, I mean, if there is lateral force, there is some response or forces that is developed in the members. What you are doing is you are removing that external force, and internally you are bringing a reaction in the brace systems. So what you do is you remove the braces, remove the external earthquake force as per response spectrum method and equilateral force you will remove. You will have this combos that is prepared. IS 1893 gives this code wherein it gives this is the way you will come at with respect to the expected value of maximum capacity of the tension and compression brace. You can see easily, you can see that the expected value of the tension brace is R by Fi into Ag, which is yield strength into area, cross sectional area is easy. This is that uncertainty factor that we talked about, that what is the maximum expected value of tension that is there in the tension member. That is what you will input here. Cmax you will calculate accordingly as per the calculations, and then you will assess them as pre and post buckle case. So what you are doing is the same beam column that you have designed as per this particular global analysis method. You will do two conditions here at local level, pre-buckle and post-buckle. Out of these three combos, you will get a maximum value of beam, you will get a maximum value of column, and that will be finalized as the beam and column element in your structural member. So let's say it's a chevron brace. I mean, this is with respect to a chevron arrangement. So chevron arrangement, if it is there, it will mostly govern 99.9999%. It will govern the design of your beam size. So post buckle condition might be governing your beam size, but maybe a global analysis may be governing your column size. So it may be a mix and match of these analysis, right? So this is how you design a final brace frame system as a whole. So you take your code, you take your structure, you locate the location of your braces. Once you have located the location of your braces, you will apply the lateral forces, uh, um, uh, either equivalent lateral force method or response spectrum method. Based on that particular procedure, you will find out what is your base shear in your structure. You will distribute that into story forces. You will use basics lead seismic load combinations, gravity load combinations. You will design your braces first. Once you have designed your braces, in which case compression might be the governing case mostly, what you will do is you will check the slenderness ratio and compactness ratio for the brace, and you'll finalize and fix the brace size then and there. You'll not change it further. To design, so once we have designed the deformation controlled element, which is the ductile element, we have to look at the force controlled element, which will be made stronger than the deformation controlled element. That is how we create the hierarchy. So how do we create it to be more stronger? We have the global analysis method where we are increasing the earthquake forces to a higher value. And we have the local analysis method where we have Tmax and Cmax and Tmax and reduced Cmax. In that basis, we will remove the braces. This particular clause is explaining the whole thing in that way itself, as to how to go about designing this particular structure. After removing, I mean, what type of analysis has to be done is given in this particular procedure. So with respect to that, you will design your beams and column element as to whichever is out of these three, global and under local pre and post buckled analysis, whichever is governing the final size of beams and columns, that is the final size you will give it, and then you will check the slenderness ratio, etc. for that. Now, if it is a BRBF, so that is the whole procedure for designing CBF system. And you will check drift and you will find out that the drift is all well and fine. Mostly it will not kind of be a problem. But two points that I want to mention is that every time when you design a structure, kindly give both earthquake and wind load combinations. If wind is totally governing your design, then there is no local, global, or anything analysis coming into picture. The brace will not undergo any nonlinear yielding or buckling. It will be just elastic overall throughout. So there is nothing to be seen in this particular case. If seismic is governing, then this procedure will come into picture. Right after this discussion, go into IS 18168, read each clause, and then you'll be able to understand why those clauses have come about. It will be very easy to understand once you understand the fundamental. Now, with respect to BRBF, what is the problem is that you understand that instead of two braces, you can give only one brace itself at one floor, and that will be more than enough. Because if it is earthquake is coming from left to right or right to left, the brace, the buckling restraint brace, have equal capacity in tension and compression. I'm not going further detail to say that okay, compression capacity is a little bit higher in buckling restraint braces. That concept we can cover it later on whenever the another event comes in. But you can understand that a single brace is more than enough for a BRB system. Now, in this particular case, the design, I mean, rather than in a CBF where compression governs, in a BRBF system, since equal values are coming, the tension may govern the design. So what you end up with is the main core element, the core which is surrounded by the strong restrainer. The core element is which is taking the tension and compression. The restrainer is just there to avoid the global buckling of the member. That local core element, the inside core element, will be of a smaller size in comparison to what section size you get for a CBF. So MRF system is a very low stiff system. The stiffness is very low. CBF is highly stiff. BRB is coming in between with a lower stiffness value. So the problem with BRB system is residual intrastory drift ratio, not just the drift value. I mean, if there is a diagonal member, stiffness increases. But after an earthquake, what is the residual drift that is left after a particular event where nonlinearity comes in? What is a permanent deformation that is left in the structure at a particular floor is more than, sometimes more than the limit for a BRB system. So residual interstory drift ratio is the main, what do you say, negative for a BRBF system, right? So once you design, yes, you have to look at residual interstory drift ratio specifically if you are designing a BRBF system. But if you are doing a CBF system, yes, more results are better, but that particular residual interstory drift ratio is not a problem for a CBF system. Now, what I said earlier, if let's say the main problem with CBF system as why we give it low response reduction factor is because shape memory alloy, yes, it is a fancy thing to give, but the cost of shape memory alloy is very huge. I mean, the amount is very high. If it comes under very low value, yes, it can be used. What I was mentioning here with respect to global responses, that the brace here, once it starts to buckle, so buckling happens very early, right? And tension yielding, as I said, it happens at around, let's say, 1% drift. So at 0.3% interstory drift, if it is a low-rise structure, almost all the braces undergo compression buckling. And whereas under, let's say, 1% drift, the yielding in the brace occurs. So there is a problem with CBF system that once the buckling initiates at one particular floor, the first floor, or where the yielding happens for the first floor, if you don't design the what do you say, the uh, hierarchy or the demand to capacity ratio across the floors, there is a tendency for this system, um, CBF system, to form soft story case in particular structures. So that is why it is not a very good system in comparison to BRBF or EBF. That is why our Indian code also says for seismic zone 5, do not use CBF system. You can go for EBF, and MRF is like 15 meters. If it is less than that, okay, you can go ahead, but not for a tall structure because drift becomes a major criteria. So I hope things are now better clear, right? Now, with respect to brace configuration, yes, I told you X brace, this is split X, right? If these are horizontals are different floors, then if I tie two floors together with an X size where the connection comes at the middle of the floor level, then this is that split X configuration, which is allowed for, permitted for SCBF. This is single story X, right? At single floor itself, I have this brace coming in. The two braces are coming here. The inverted V or the chevron configuration, and this is the V-type configuration, right? These are the ones which are permitted. These are the ones which are not permitted, right? You can see for this particular base, we call it as a K brace system. The problem is it comes at the middle of the column. So you have unbalanced forces occurring at the middle of the particular important element like column. So you avoid such kind of K kind of system. Same explanation is here. This a single brace is not going to work, right? It may, if it is from right to left, it works. If the earthquake comes from left to right, this will undergo buckling. So buckling load is not enough, and your beam columns will be strained too much in terms of taking the lateral force, and it may collapse. So that is why this kind of configurations are not allowed. And one more thing you have to understand is key. One important thing is while designing, yes, we talked about lateral forces being considered, etc. Under gravity, you have to ensure. See, you when you design, let's say, chevron arrangement, under, let's say, gravity, dead load and live load, you have a combo 1.5 dead load plus 1.5 live load. You have to understand that these braces at one point in time after an earthquake is going to get damaged. One brace might be totally yielded and it may fracture at a later point, and one brace might be totally buckled kind of a condition. So you do not, I mean, if I model this system as like this itself, I might be getting an advantage of the beam size for this one, saying that this is getting supported at this location. The chevron arrangement is supporting the beam at the mid location. So my span of the beam is getting reduced. But what you have to understand is, even before or after the entire design, what you have to ensure is, do not take the advantage of the chevron arrangement or the inverted V arrangement in any case for the beams and columns to carry the gravity load. So the beams and columns should be good enough to carry the combos related to gravity load, and the earthquake ke liye you can bring it on after that to design your braces, and then again check the size of beams columns as per global and local analysis. Right? I hope you have understood. That is what the code says. Our code doesn't mention it specifically, but if you look 341.16, it says that do not take the advantage of the braces for the beams and columns to carry general gravity load, because once the earthquake happens, there may be major damage in the braces. It may fracture, it may not fracture, but the beams and columns should be good enough to carry the gravity loads. So these are some events, like this is the Christchurch earthquake, and you can see the failure that has happened in the chevron arrangement. Here the beam has not failed, but there is a net section fracture that has occurred in the braces, right? Again, this is related to the unbalanced forces coming into picture. But here, rather than the beam failing, the beam sizes are very low, but the connection design has been done very badly. This is multi-story X-brace frame. Now here also, you might say that the best way, the alternative for inverted V is to give a kind of split X kind of arrangement where the imbalance force is getting balanced by two braces on top. But you have to understand, if one of the tension braces fail during, let's say, an MC level earthquake or something like that, that imbalance force will again come in. So once you design the structure as per the requirement, you have to ensure that things are, I mean, you consider all the worst case scenarios for the braces to assess the capacity of your beams and columns. Now this is single X, right? You have to understand, like, when once you give the nonlinear analysis, if you're giving for a single story X, you have to understand that if you're connecting the single story X at the middle, what you have to understand is the hinge mechanism that we earlier talked, right? In a brace, it comes at the center. If if it is an X shape which is connected at the center, the hinge will not form at this location, but it will form at the mid length of each of these four braces that are getting formed. So if you do a mistake in terms of, let's say, you understand every nonlinearity 4117, you know how to model lumped plasticity, you know how to do anything and everything. The main problem is if you don't understand where the nonlinearity is going to get lumped at, or where the nonlinearities get initiated, your assessment will go totally wrong. So for an X-braced frame with the connection at the center, the effective brace length or the buckling length reduces. So it will buckle like this in this location, and the hinges will form at the mid length, or the length is given by the code, but that will form there. Like this is an example of that X-braced frame. I mean, this is not the one that got damaged, but these are the kind of construction that is done in Japan, etc. Whereas you can see here in the X-braced frame, this is the length at which, so it is connected. The brace is diagonally connected at the center, so the hinges forms at this particular location, right? So that is clear now. In braces, where should we have to provide hinges? Miss or middle or end? See, again, the question is wrong in a sense that at the end, I said if there is a gusset plate that you're giving, a thin gusset plate meant to undergo maybe out of plane buckling, or a knife plate which is able to undergo in plane buckling, out of plane stiffness of those 6 plates are nothing. So you can give a moment release there. So the next is, if there is a single brace, if there is a single brace like if there is a single brace like this, the hinges will form at the middle of the brace. But if it is like a single story X type of configuration connected at the middle, Listen to my sentence carefully. If it is connected in the middle, then the hinges are going to form at these locations as observed in this figure, right? So, उस case में you have to carefully model your system, etc. Now, these are some fun facts saying that 85 to 90% of the original elastic stiffness and resistance is generally provided by the braces. At 1% story drift, uh, let's say at that time 1% means some of the braces would have yielded as well as many of them would have buckled. It still resists about 75 to 85% of the lateral load. At 2% story drift, the braces resist 60 to 70% of the lateral load. So some stiffness not in terms of stiffness, but the strength and all are reducing, right? So considering that, you have to do the assessment, but these are the ratios in which certain things are happening. Braced frame retains 20 to 40% of maximum resistance after all braces in a given story are fractured by virtue of beams, columns, and gusset plates. Now, gusset plates, even if the brace fractures, the gusset plate is there connecting the beams and columns. So even if a pinned connection is given, but a gusset plate is there, it still adds to the rigidity of the connection. So there are some things which we are still ignoring in terms of our analysis. We give pinned connection. If we give moment release for the gusset plate, it might not be considering all the cases into it. Now, here is the time history analysis of all these configurations that are there, 3-story, 6-story that we had done as per our study. And we have understood in a case that case in local analysis where you consider all the braces at all floors to have yielded and buckled simultaneously is a rare fact to happen. Normally what happens is you can see this is an 18-story structure and you can see only at a particular floor level, a mid-floor level as well as a top floor level, the demands are higher. So you can expect the braces at those levels to undergo yielding and buckling with some distributions. Like there also demand to capacity ratio has to be controlled so that it doesn't happen at from one floor itself. But you can understand that at this particular location and at this location, let's say story number 3 to 7 and then 12 to 16 to 17, it happens that you will get yielding of the braces and buckling of the braces with intermediate levels braces not even performing anything. So you can understand the local analysis and global analysis and everything to design your beams and columns is to take the worst case scenario. But as a researcher, as future researchers or things like that, you can try to optimize the requirement as to be okay, there may be a midway in between, but then a lot of analysis has to be done to understand all those various cases, right? Ends. Rohit, I think I have answered, like we have to provide it at the periphery because of the two advantages that it gives. Now, this is a general category of where we give the braces in one particular panel, and this is the staggered arrangement. Now, one problem is staggered may you may think that okay, the lateral force resisting system is not in continuous in plane continuity is getting kind of, I mean, irregularity case that we have in 1893. This is violating the in plane regularity condition. But what advantage staggered one has is because if you have the braces arranged along one particular bay over the height, the foundation forces are going to increase more here. So whatever foundation design will be there for these non-braced bays will be much lower than what you have for a braced bay. Whereas in this case, it gets distributed among these three columns. So there is a problem that, okay, if you go for staggered arrangement, Tremblay, I couldn't read it, Dr. Narayan. Maybe we can discuss it at the very end. Now, these are some problems with respect to this is net section fracture here. This is if you don't design the end connection between gusset plate and beams and columns. If you have, then it can fail here. Then some good design, good in a quoted way, saying that it is a very bad design that you have here. These are the state of connections that we have. One small thing I think we have, let me take like, let me go slowly itself. Like we have not yet detailing part, we are just going to cover right now. So we talked about brace, we talked about what we want from the brace, and we talked about the role of gusset plate coming into picture as it can undergo out of plane buckling or in plane buckling as per the requirement. Now, current code, American code gives a requirement of something like, okay, you can understand the design of gusset plate in a sense that if I cut a slit in brace, the amount of length that I have to insert into the gusset plate would be based upon how much strength I would get from that particular connection. So let's say I cut a slit, idealize when I say that I cut a slit in the brace on throughout the top and the bottom plate, and then insert my gusset plate means I have 4 faces for welding the gusset plate to the brace. So I do a fillet welding, let's say, and I consider that, okay, 0.707 multiplied by the thickness of the weld multiplied by the allowable yield stress of the weld or the stress in the base metal, whichever is lower that we call upon, and then the length of the weld that I take upon, if it is equal to the maximum capacity of the brace. So normally connections as in steel structure that we do, we design based upon the maximum capacity of the member that is getting connected. So we have the equations for finding out, let's say what we discussed earlier, RYFI into AG is a maximum tension capacity that will be transferred from the brace to the beams and columns. So the same value with some hierarchy, if you want to keep, the codes might be giving. When you read the code, look at extra numbers, maybe 1.2, maybe 1.1, they add extra, and they create a hierarchy between, okay, brace to connection and then brace to column beam connection. So you design that particular thing, and currently what the American code says is once you decided how much is the insertion length of the brace into the gusset plate, you give a linear clearance of 2 TP here. But there are study by Lehman and Reuter which gives like they have a better calculation and which reduces the size of the gusset plate and says if you give an elliptical clearance of 8 TP, that would perform better, as well as, I mean, there is nothing wrong with the performance of this. The only case is you are wasting a lot of steel plate by giving this linear clearance. I mean, I can say by word only, but if you design, I mean, this particular, there is a paper by Lehman and Reuter that is available where the entire design procedure for the elliptical design is given totally. So you can use that and do the design as per, or you can follow the code as per American code and do your design of gusset plate as such. So linear or elliptical, it provides in a, I mean, it functions in a better way. Now you can see a connection here at this particular location. So earlier, I mean, there has been an evolution with respect to the design of gusset plate also, where you can see that the middle gusset plate, this middle gusset plate has been enhanced here. You can see some additional stiffener plate that is given at the edges, right? So what you have to understand is, last time we said, if the panel zone yields along, I mean, limited yielding is happening in the panel zone and it happens along with the moment frame beam, then it is like two people are fighting the same enemy, which enhances the overall capacity. If the panel zone yields, it delays the fracture of the beam element and enhances its performance to a larger drift. The same way, if you increase the thickness of the gusset plate or you add additional stiffener to the gusset plate here, it reduces the outer plane movement or the bending or yielding of the gusset plate, which makes more kind of energy dissipation uh, onus to the brace element, and the brace element can fracture early if your gusset plate doesn't bend adequately. So such kind of arrangement have been removed. You can go with a normal steel plate as it is, but you can see like in a middle plate connection, in a middle plate, you have two braces coming and hitting this particular location, where you have, I mean, at a corner, it is either the brace is giving a tension force or it is giving a compression force. But at a middle plate, the same plate is subjected to tension as well as compression. So you have this gusset plate being stressed more than what is being done at a corner plate. So to kind of better the performance, you can see two stiffener plates, right? You can see here one right on top of my cursor, the second one here. You can see one here and one here, and you can see the same thing here. This is the one vertical stiffener here. This is the other vertical stiffener. This is something for this. Uh, don't include this in your visual. This is for some LVDT attachment for the experiment or something like that. But you have two stiffeners. What is the function of these two stiffeners? Is to isolate the performance of this cassette plate from the other one. If you don't have stiffener, this plate will be stressed more and it will get fractured. But if you give additional stiffeners here, then it will be like to isolate the two, not purely 100% isolation, but it has been observed that this kind of stiffness enhances the performance of this middle cassette plate. Another thing is like elliptical 8 TP clearance, a linear clearance idea of 6 TP is what has been observed for a improvement of middle gusset plate. So when you go into design, yes, Indian code IS 18168 doesn't give any detailing practice as such, but you can go to American code ASC 360, 341. There, this particular detailing procedure has been given, and you can, I mean, without fear, you can use it to design your structure. There are, as I said, Lehman and Reuter gives the design of the gusset plate. There is a thesis, Clark 2009, which gives the design of the gusset plate for buckling also. Like, how do I calculate the buckling capacity of the gusset plate after the brace length has come in? So you have some length of the gusset plate that is there beyond which the brace actually comes in. So the brace, when it undergoes compression, will apply some compressive force here. So to avoid buckling of the gusset plate, the Lehman and Reuter paper, if you go, there is one paper based on ductile detailing of gusset plates or something like that. In that, you will find out these calculations to be given. So you take an average of these lengths. Whitmore width nikalna hai. You have to find out Whitmore width based on, I mean, Whitmore width is nothing but the point where the brace starts its insertion. You give an angle of 30 degree, 30 degree. At the end of the brace, you put a straight line, and where it matches with the 30 degree, the end location, you provide a perpendicular line from that point to wherever it connects with the end of the gusset plate. At the mid location, you will find one more length. At the end location, you will find one more length. The average of these three lengths over the Whitmore width is used to find out the effective length of the gusset plate for finding the buckling capacity. So references are given in this particular thesis. I mean, this particular slide, you can go to them and then go ahead with this. Now, one more thing is, like last time I said, na, ki once you do experiment, you put whitewash on it, and if you the whitewash, I mean, if the flakes come out, it gives an indication of where it has yielded. So the ATP elliptical has come from such a kind of experiment, which shows that okay, when a gusset plate bends out of plane, the flakes are in such a way that it has yielded, or the yielding has happened only in these locations. The rest of the locations are okay. So that has come about with respect to design of these things, right? Now, yielding in connection is highly desirable because permits end rotation of buckled brace, allows brace to develop larger inelastic deformation prior to brace fracture, maintain consistency with brace capacity assumed in connection, reduces the demands on weld connecting gusset to beams and columns. You can read it. I've given the answer here, all true except F. We have only, I think, 10 more minutes. Fun exercise, you can read them. I've given the answer also. I mean, this is the same in terms of this. These are some connections with respect to, let's say, this is with respect to Christchurch earthquake that we have had. Again, the brace has different types of connections. This is wrong. As I said, the gusset plate should be allowed to kind of bend out of plane or in plane with a knife plate or things like that. Anything, any stiffener. I mean, newer designs, you won't be finding any kind of such kind of approach. These are the connections that are provided in some structures. You can see the lateral bracing, horizontal bracing. Our code officially gives as to where we should give this horizontal bracing in a CBF system. In a moment frame, you already know that after the protected element over a length of 2 dB, then only you give the horizontal bracing, etc. Right? Now, this is nothing but another balanced design procedure. Again, Lehman has proposed this particular thing. Current code, I'll show you. The current code is like this, where you can understand. See, this is the procedure. I'm not going to rush at all. I'll take extra 15 minutes, but I'll not rush. What is this particular procedure will inspire you to think more about what kind of design or research that you're doing. A procedure is very good in a sense that whenever we look at, let's say, design of bolt systems or design of any kind of connections, what do? Is we find out what is the demand on coming on the connection. Then we have a list of failures that we have said. Let's say bolt fail in shear, bolt fail in bearing, bolt fail in tension. All three things are there, but we don't know, like we are trying to ensure that the failure does not occur at that particular level, or the forces are much, I mean the strength is much higher than the demand that is coming. That is what we ensure. That is how the current code guidelines with respect to design of connection is given, whether it is our code or whether it is American code. This is how they follow. The balanced design procedure is something that I have seen that even in our moment frames as well, this particular thing is to ensure that what you do is you list out, let's say if you have a system, you list out what are the yield mechanisms that you expect in your system and what are the failure modes that you want. So what you do is you apply factors in such a way that you are giving weightage to the event that is happening also. Here there is no weightage. It is all about the strength being higher than the demand. Here, even when the strength is higher than the demand, you prioritize certain event to happen first. So let's say I want certain yielding of the plate has to be my priority number one as to that is the event that I have to happen in my connection means I will give it the lowest factor of safety so that that event occurs first. If I have a brittle failure event that can happen, I will give it the highest factor of safety such that it is pushed backward. Right. So some kind of that is the name of balance design procedure. This procedure you will find in Lehman and Reuter has used it for design of gusset plates, etc. But you will find it at different locations as per uh, I mean even in your design, let's say I want to design my connections for a moment frame. Now you understand the beam will supply the maximum capacity to the panel zone. From the beam to the column it will go, but in between there is connection and panel zone. Do you want to give hierarchy to the strength at which you design the connection? So last time we saw if I design the panel zone with 1.3 factor, the panel zone yielding is getting reduced and yielding in the beam is getting enhanced. So some way it works out. So some additional codal provisions with respect to SCBF. It says SCBF member shall be concentrically connected, but eccentricities, how much concentric it should be to be called as concentrically braced frame is this line. That is, eccentricity should be less than the beam depth. If it is less than that, it is still a CBF system, right? And rest of the sentence, if you read now, you will understand. SCBF designed in accordance with these provisions are expected to provide inelastic deformation capacity primarily through brace buckling and yielding of the bracing tension. Now you understand everything. This is that particular clause related to the unbalanced forces in a chevron arrangement or the local analysis, right? To remove the braces and consider two cases as pre and post. That is this A and B. Multi-tiered brace frame is another version of CBF system. I have images for it and you will understand what that is. This is the capacity, expected capacity under tension and compression for which you will design the force controlled element. That is this particular thing. And inverted V and inverted case ke liye, what are the conditions that are there is given separately. Braces, lateral force distribution, braces shall be provided in alternate direction along each line of brace. You know why alternate now. Once we have understood the logic, the codal language becomes very easy for you. Along any line of brace, braces shall be provided such that lateral force in any direction shall resist between 30 to 70%. So it is your choice whether you want braces to be the big hero or should be a kind of a combined kind of a thing where another system is also there to take up the lateral forces. Protected zone, yes. The protected zone is the braces, like the main element, braces, the center 1/4 of the brace length, and zone adjacent to each connection of the brace depth in the plane of buckling. So you don't, if some, I've seen some drawings where the brace element is made with built-up channel sections or angle sections, but they have used splice or lacing elements very randomly such that their cables can go through that brace element. So such kind of things happen even when the earthquake was governing. So I was saying you have to take care in terms of the protected zone. And then slenderness ratio, I was saying 165, but it is 160 that the value gives. The effective slenderness ratio shall be of less than 160, right? Then you have effective area. This is net section area failure related to this clause is related to net section failure. So if you read, you will understand what I'm saying is once we have understood that what I want from the system, things will be very easy. Now this is a multi-tiered brace frame, right? You understand that if you have an industrial structure where the inertia forces will come from the top of the roof of the structure, there is no intermediate floor level, but the column height is let's say 12 to 16 meters, then you cannot give a brace which is so long, very long, which slenderness ratio will be very high. So intermediate beams you will give, and you will give a multi-tiered braced frame where the inertia will come only from the roof level. That is this. This is a mega brace frame system, right? Pulling all the floors from, pulling forces from different floor levels, right? Is there something wrong here? You can understand what is wrong there, as the brace, if it buckles, it will also damage the, what do you say? The wall elements will fall if it fails. Now, looking at the failure mechanism, yes, you can understand. This is very easy to understand. We'll not go through this. Let me, we have very few slides for EBF systems, but it is easy to understand once you've understood the CBF systems, right? So in EBF, first case to understand is what is the capacity, what do you say? The deformation controlled element here is the link element that is given here. Rest, beams, columns, and braces are the force controlled element. So in this case, the brace is not undergoing any yielding, no buckling, nothing. It has to remain essentially elastic under dB level, etc. that we have talked earlier. So the only deformation controlled element is the link element, right? Second important point. I mean, I'm not rushing through, but to tell you the important points, the two things are there are two major configurations that are normally used. One is the link to beam connection, and one is the link to column connection. This is the most popular kind of connection for EBF system. Understand, this is what our code recommends as the system that can be used in high seismic region like zone 5, right? So in this system must be doing something good in that term. So what you have to understand is link to column is the more prone to column damage. Like anything where non-linearity comes in, you have a problem if it is attached to the column, like the K-braced element. The column getting damaged is a more severe case rather than this particular case. So that is why the this type of an arrangement is the left side one is the more preferred arrangement. There is one building in Calcutta that I know of, which is an EBF system in India. The first one, I think, Insdag was part of it in terms of its making, or I don't know, design part, I don't know. But in Calcutta, there is an EBF system in India. Very rare to find, but this is the best ideal system. There are different variations of link element. You can see the link element is this here, this one here, this length here. This is recently getting popular in a sense that if I give a link element like this can be removed after an earthquake and replaced with another one. Whereas in this case, this will be part of the beam itself. The slab will be there. Yes, no shear studs will be used in the deformation control element at this location. But then after an earthquake, the problem will be to remove and replace and put it. So you can understand during an earthquake, this particular link element will be undergoing nonlinear deformations. We'll uh, discuss as to what it is, as to what type of a nonlinear thing is going to happen, whether it is yielding in flexure or things like that. But you can understand that there is some kink that forms, right? It can damage the floor also. Cracks can occur in the floor also. So you have there is a limit given in the code with respect to how much rotation should be allowed for the link element. Maximum rotation also there is a limit onto it. Now, this is the most important slide that you have to understand is you have understood what is a link element. Let's say this is the link element, that small element between those brace element is what is given here. So you can understand that when a lateral force gets applied here, let's say moments are getting applied, shear forces are there. I can use the couple this thing, right? MA plus MB is equal to the shear force into the link length, right? So what we can say that the link length is equal to, if MA and MB are same, it's equal to 2M by V, right? Twice M by V. And we can have an ideal condition wherein the link, let's say it is yielding and reaching plastic moment capacity in flexure, as well as in shear, it is reaching its plastic capacity VP, means for a balanced condition for both flexural hinge and shear hinge getting formed, E is equal to 2 MP by VP. Now, what the people who have tested, who have said that, okay, the if we consider strain hardening, the flexural capacity, sorry, shear capacity may reach up to 1.5 level. And they also put a limit key, okay, if my rotation, flexural rotation in the kink element is there, I should limit it to 1.2 times. So 2 into 1.2 MP divided by 1.5 VP comes somewhere around 1.6 MP by VP value. So what it means is my link element, if you look closely here, my link element can be anything. So this is like, if I take my brace to this location, it becomes a moment frame. If I spread both these braces to the corner, it becomes a moment frame. If I make it meet at the center, the braces, it becomes a CBF. So EBF is somewhere in between. In that case, this link element, everything like this nonlinear performance of the link element depends upon what is the length of the link. If the length of the link is very large, then flexural hinges will develop. And if the length of the link is very short, then shear will dominate and shear hinges will form. So what this ratio gives us, if my length of the link is less than 1.6 MP by VP of the cross section of, capacity, MP and VP is the capacity of the cross section. It may be an I section, it may be a box section. Us basis mein, if I find out this ratio, if the length of the link is less than 1.6 MP by VP, then it is a short shear link, and shear yielding, I mean yielding by shear governs the performance of the link element. If it is more than 2.6, then shear yielding will not happen. I mean, this is wrong here. It's flexural yielding will happen. And long links, it is called long link, and flexural yielding is what happens in a long link. If it is 1.6 to 2.6, then it gives a mixed kind of a performance wherein the link element may form flexural hinge as well as it may form a shear hinge as well. And you should understand one thing, that contrary to last time what I said is contrary to RCC where shear is I mean, not a good behavior. Like we said for panel zone, the performance of a steel under shear, pure shear kind of a condition gives a better and stable energy dissipation than in a flexural case. A higher energy dissipation is expected. So the best is if you can give a short shear link, right? The main point I want to put you across is based on the length of the link, either flexural or shear or both can form, both hinges can form, which is ultimately leading to how much energy it can dissipate. The shear yielding and shear deformation is more stable in steel structures. That is why we prefer short shear link to be given. And while giving a link, we would prefer link to beam connection rather than link to column kind of a configuration. So it's clear that is a main point that I want to put across. How do you design a EBF system? As simple as the earlier case. You have a system, you have a EBF system there. Along all floors, there is an EBF system. You find out the lateral forces, equivalent static method or response spectrum method. You use basic seismic combinations and you find out, you design the link element. You already know the cross section that you're giving. Let's say you start with a cross section of the gravity beam itself. You find out what is the shear capacity, what is the link length. I mean, is it less than 1.6 MP by VP? Then you know that shear hinges are going to be formed. If it is shear hinges, then the maximum capacity of the shear hinges is what will be used for designing the beams, columns, and braces, right? So here is the case where a column tree has been formed. When you model it, yes, this model is unstable. If you give loading like this, you have to give some boundary conditions at each floor level. Such that now what I'm doing here is, this is a short shear link and the maximum shear capacity of the link element, maximum expected value that your link element can give, including all strain hardening, material uncertainty, whatever expected value that the code says. On that basis, I have to find out what are the forces that I have to give. Based on these forces, I will find out what are the levels. There is no pre-buckle, there is no post-buckle, there is no analysis like this. There is only this kind of analysis, that maximum capacity of the link has to be used to design for the force controlled element as it is. You can use a column tree method as it is and go ahead with this. Yes, the hinges that are formed, normally what is happening is, here the brace element can be directly welded also. There is no need for a gusset plate. So normally the link element may be either having flexural hinges or shear hinges. There may be hinges forming just outside the link element. There have been instances where such kind of hinges are getting formed. If your beam to column connection is rigid, then hinges can form here as well as here, and then at the base of the column it can also form. So that is how the hinges form in this particular element. Now quickly, if you have a link element, which is like, you think like the beam is continuing, whatever beam you have, that same beam is continuing. Let's say this is an I section. You can see that this is an unstiffened link where in the link length, which is a short shear link kind of a span it has no intermediate stiffener, means a long plate undergoing pure shear kind of condition, and you can see diagonal compression and tension forming in terms of this thing. So this is compression, so that is why buckle shape is forming like this, and the other diagonal will be having generating tension. So you have stiffened link. What is the benefit of this? If you stiffen a plate which is undergoing shear with different stiffnesses, is like it divides it into different panels. Now the compression length is less. It buckles. Buckling strength has increased, and then tension stiffening effect has also increased, such that you can see the hysteresis curve between the two. Right, one is not that much good, and stiffened link. You will find out codal clauses with respect to stiffening of the link element. Now, if you look at this particular, this is important to understand, is this is an experiment that has been done where whitewash has been done totally on the link element. Look at the image and try to understand which is a shear, which is a link where shear hinges, or a short shear, which is a short link, which is a long link, and which is an intermediate link, right? A short link is where the shear yielding in the panel has occurred. A long link is where flexural yielding of the link element has occurred, and a panel which is intermediate, where both shear and flexural hinges will form. So if you look at the diagram closely, you will see that the flanges here are, the whitewash is intact, nothing has happened to them. But each panel, the flakes have gone out. The whitewash flakes have gone out. So this is a pure shear link. If you look at this particular element, you can see local buckling at the ends of the links, right? The shear panel here and here, the whitewash is still intact. Here, a little bit it has gone off. So this is the long link where the panel has undergone flexural hinges. You understand beam column connection in a moment frame. This is how the local buckling image that we saw. And this here, if you see, this is the intermediate one where each panel, if you see, the flaking of whitewash, again, I'm going to explain that. I'm not saying that when it has yielded or has it yielded question is a different issue. You have to put strain gauges and other devices, but this flaking of the whitewash is giving an indication that here some kind of deformation has occurred and yielding is predominantly happening. So if you look at this intermediate one, all the shear panels have kind of, let's say, yielded, and you can look at the end panel element. Local buckling has happened, some kind of buckling, local buckling has happened in the flange as well as in the web panel as a whole. So this indicates both the flexural hinges forming at the ends, and then shear hinges are also, like the total plate has yielded under shear also, right? So that we have to think about. Now, required strength of capacity protected element shall be determined based upon, this is capacity protected element design के लिए 1.1 RY into SH. Strain hardening factors are, to design the force controlled element, what is the force level of, how to calculate the capacity of the link element is given here. This clause gives the maximum rotation limit of this thing, and bracing shall be provided. Like wherever the link elements are there, at the ends of the link element, your horizontal bracing should come, right? So these two locations. So in a moment frame, it comes at the ends of the plastic hinge in the beam. At that location, you have to give anyway. There are two types of horizontal bracing you have to understand. One is with respect to the requirement of lateral torsional buckling of your primary beam. The second is with respect to near to the inelastic location, inelastic hinge, where instability might occur in that particular region where the plastic hinge is forming. So in a moment frame, if you read the code IS 18168, it gives the location after 2 dB distance where the horizontal bracing for the plastic hinge has to be given. In brace, it tells you provide right at the middle where the joints are forming. Let's say in a chevron case, right at the middle of the beam, you provide a horizontal, irrespective of whether the beam requires it for a lateral torsional buckling or not. There instability can occur, and it is better to give a horizontal bracing there. Same way for an link element, bracing shall be provided. Horizontal bracing shall be provided both the top and bottom flange of the link, at the end of the link for the I-shaped sections. At both ends, it has to be given, right? And protected zone for EBF are the links. Use of shear studs on link is prohibited. You know what is the reason, right? So that brings us to the end of the presentation. This is our laboratory in earthquake department, and this is just an information like what we have started in January. This is like, we understand that most of you don't know the total design procedure, whatever we have talked about. You have some experience with respect to Tajul in terms of nonlinear analysis of RCC structure, let's say. But for steel education and steel design, we are running some courses, online courses. We are contacting certain international professors in terms of giving their purview about what is recently happening as to how the codal are this thing. So this is one of the webinars that is scheduled on May 21st. It's all free of cost. We are requesting, that's why we don't have frequently such lectures, because we contact them without any monetary benefit to them or any remuneration. It's their goodwill that they are giving us these lectures. He's on May 21st, we have Lignos, Professor Lignos giving a lecture. He's a senior professor at EPFL Switzerland. He's a very good professor. He's top of the game right now in terms of this thing. So if for you to register, there is no cost at all. You can go to Steel Edu Forum, register there, so that future events, like we'll be conducting certain design classes also, in terms of hands-on design classes also. So if you register, you will get some information from there. This is an online webinar on May 21st. His topic is on seismic stability of steel moment resisting frames, recent findings and implementation in design standards. So this is going to be he's one of the best professors right now internationally. Other than that, we are I mean, rather than always going into international codes and inspiring our codes from there, at my end, what I'm doing at IIT Roorkee at Department of Earthquake Engineering is we have started looking at our steel, E250, the E350, and 450 as to what their ultra low cycle performance are. We are also looking at in terms of welding also. Like it's not enough to look at just the base metal. We have to look at different types of weld grades. I mean, normally we do same grade of steel to steel, but we are even looking at mixed grade of steel. Like if my columns are force controlled and beam is deformation controlled, then and most of the time, if my column has to remain elastic, then why do I care to give the same grade of steel if I can control the property of steel? I mean, it's a concept which has to have confidence from the manufacturer's side, such that he gives a controlled product at our end. I mean, the material uncertainty should not be very high. It should not be this thing. You can use, I mean, the code does not recommend, but future is there in terms of using higher grade steel for a force controlled element, which will reduce the cost of your member. Then we are doing in composite systems, we are doing something, and this is what we talked about. Can I give steel braces to RCC connection? We are doing with respect to post installed chemical anchors. We are doing an understanding key. How can we connect it efficiently such that we get a better performance? So this is one full story 5.5-meter height RC frame with plinth beam model, plinth beam installed, and then steel braces have been used to retrofit. So this is the bare frame design, and this is a retrofitted frame, which gives a better response. I mean, so it is like the question is, yes, we can give steel braces to new as well as older RCC construction. We have also done testing with BRB, and in-house BRB was prepared, and testing has been done, and you can see the RC bare element is this, and the RC BRB is giving higher energy dissipation. The graph has not been refined, so you can see the vibrations across the testing, etc. So we have to do some local retrofitting also. Like retrofitting of RCC structure is not so easy because you have to understand what has been provided already. So some local retrofitting might be also required. Some studies are being done on cold form steel also. So thank you everyone for the patience. Put on much.
Thank you,
I
sir. Now we can go to question answer session.
oh,
Whatever
okay,
question is there on the question box, that we can start one by one.
okay. Kindly explain the structural analysis, including nonlinear mechanism of BRB. It will be a great help. So, see, understand one thing is the same concept again goes into the analysis. Yes, there is no pre and post buckled analysis in this particular case. BRB yields in tension, and let's say it buckles in multiple modes in compression. But if you look at the backbone curve, it will be like both tension and compression will be equal. So उस case में even the yielding, I mean, you can give hinges at the center of that particular brace element, and you can go ahead with respect to designing of a BRB. It is much easier in comparison to CBF. There is no pre or post buckle analysis. What I suggest you, Rena, is there is a book for everyone. It is like Ductile Design of Steel Structures by Bruno in 2011. It's a very good book in terms of understanding structural system. It has all steel systems: CBF, EBF, BRBF, steel plate shear wall, steel truss moment frame, all kind of steel structural systems. Basics are given there. Once you go through it, it's a big book, but if you go through it, you will be able to understand all codes from all countries. So, Rena, I suggest you go through that particular code, but it's one. Dr. Narayan said bit more gazette plate design. I don't understand. Yes, what
Sir,
I
hello.
ha Tajul.
Sir, I just want to add one thing.
Hmm.
I think these questions we can prepare an answer sheet and share with them before starting with these questions. If participants have any questions to ask, I think that we can take first.
Okay. Apart from these questions, does anyone want to ask directly one question right now?
Yeah, that is what, because in earlier sessions we did same thing. Participants have many questions at the end of the session, so that we can take first. And
Okay.
whatever questions is in the chat box, that we can prepare the answer sheet and share with them if we do not have time to answer at this session.
Okay. Do you have any
सर
questions?
यस सर सर अगर हम एनालिसिस करते हैं किसी भी बीआरबी का या फिर किसी भी ब्रेसेस का, तो हमें ये कैसे पता चलेगा कि पर्टिकुलर इंडिविजुअल एक ब्रेसेस के थ्रू कितना एनर्जी डिसिपेट किया है?
नहीं, उसके लिए आपको रोहित आपको क्या करना है, like what you have to do is, let's say you're providing a hinge in the element, right? Nonlinear
यस सर.
hinge, if you're giving. So after the analysis, you have to go back to that particular hinge and see how much that hinge has deformed in the overall system. It will give you a hysteresis curve itself, right?
यस सर.
If you get the hysteresis curve, the only thing is go to MATLAB, write a code to find out the area inside each particular curve, and it will directly give you how much energy each element has. If you have applied the hinges at correct locations, then if you calculate the area under each curve, then you will get energy dissipated by each element at each location.
Okay.
Right. So
Thank
it's
you, sir.
more about applying the hinges at the right location, applying the correct backbone curve from 4117 appropriate to that particular element as to how, let's say if it is a link element, it is undergoing shear yielding, but you gave it a hinge for flexural yielding. That is wrong. So if you give for shear yielding, once the analysis has run, whether it is pushover or nonlinear time history, those hinge results will be already showing you how much it has deformed in each cycle, how many cycles have occurred, etc. You extract that result, find out area under the curve, and you'll get the energy.
Okay, thank you, sir.
Okay, Rohit. Any other questions, guys? Dr. Narayan, you have, I saw many questions, lengthy questions from you. I couldn't read it at that time, and
Good evening, sir. Sir, actually my network connection is weak, so that's why.
okay.
Sir, I have two main questions regarding the chevron brace. Sir, in X brace, we have both ends connected to beam column, the brace ends
Joint.
connected to beam and column.
Correct. Dr. Narayan, I can't hear you now. I think, as you said, your network is weak. Can anyone else ask till Dr. Narayan comes back?
That the buckling will happen at the middle.
Dr. Narayan, I heard only about X brace at ends and buckling at the middle. In between, everything was something happened with your network. Can you ask your question again? Can anyone else ask till Dr. Narayan comes back?
यस सर. सर आपने एक बताया था कि बीआरबी का जो डिसएडवांटेज है वो रेसिडुअल ड्रिफ्ट है. सर वो पार्ट समझ नहीं आया था कि आप क्या कह रहे हैं. मतलब रेसिडुअल ड्रिफ्ट है तो उससे क्या प्रॉब्लम है?
नहीं, रेसिडुअल ड्रिफ्ट पहले तो रोहित ये समझो कि आप वो पार्ट समझ गए होंगे ना कि इफ आई डू अ टाइम हिस्ट्री एनालिसिस विद अर्थक्वेक, आई मीन नॉन लीनियर टाइम हिस्ट्री एनालिसिस,
यस सर. यस सर.
once I have finished my analysis, let's say 30-second का earthquake था, I finished my analysis and I find out that after the structure has come to a standstill, there are certain portions which are certain locations, certain floors में कुछ residual drift आ गया है, like it's permanent set, like some non-linearity has come into picture, and once non-linear deformation has happened, it doesn't bounce back to its original shape, right? It will have some kind of that final deformation may be due to non-linearity in any element. It may be brace, it may be beam, it may be column, anything. So what you look at is you look at the results at the end of the analysis as what is remaining. I mean, you can extend. I mean, it cannot be earthquake right at the end of the earthquake. You extend the earthquake time history by adding few more points. Time is increasing, but no amplitude is there. So you will find out that what is remaining there. Now, what I was telling with respect to the structural system as such is, let's say when you have lateral forces, story forces applied on the structure, you have some axial force in the brace members, I said. In CBF, when you design, your compression is governing the design. So, मान लो, my compression value, let's say I apply forces from the left at particular floor. One brace is in tension, one brace is in compression. If you do analysis yourself, you'll find out that the tension value is, let's say, 1000 kilonewton. the compression value is somewhere around 600 kilonewton or 700. Now, when you design for compression, your buckling ke basis pe, the 700 capacity compression ke basis pe, the brace that you design, its tension capacity might be 1400 in comparison to your 1000 kilonewton of demand, right? That is where the brace section that we design for a CBF system comes much higher in size. Now think of the opposite case. When you have a BRB, your tension compression capacities of the section are the same. So regardless of whether tension governs or compression governs, when you design that kind of a system, let's say it is 1000 kilonewton and 700 kilonewton ke basis by, let's say tension compression is again coming, your design will be governed by 1000 kilonewton only. So your total capacity when you design, you might not be taking 700 kilonewton as buckling. So it is 700 is the compression demand, 1000 is the tension demand. In BRB, 1000 governs the design. So based on that 1000, when you design, you might be ending up only 1100 or 1050 because you are designing as per the cross section that is available. So normally, I'm saying this is a condition case that I'm talking. So what happens is you end up with a larger brace section in a CBF system and you end up with a lower size section in a BRBF system, right? Again, one more thing, you don't need two braces in one floor. You need only one brace for the BRB at one floor. So again, the stiffness part is decreasing for a BRBF system in comparison to a CBF system based on the size of the element and based on the number of the element that you have as a BRB component. So in the end, what happens? Stiffness decreases. So for the same earthquake, or let's say same earthquake नहीं, मतलब building का analysis करेंगे तो उसमें जो डिफॉर्मेशन आएगा वो BRB में ज्यादा आएगा in comparison to CBF system. CBF is relatively more stiff. So that is why residual interstory drift becomes a problem for BRBF system.
सर
रोहित,
बट अगर हम बेस्ड ऑन द डिमांड अगर बीआरबी को डिजाइन करें डिस्प्लेसमेंट बेस्ड पे तो भी ये प्रॉब्लम आएगा।
नहीं, डिस्प्लेसमेंट तभी भी डिमांड नहीं है ना रोहित. व्हाट आई सेड इन द बिगिनिंग इज BRB इज एडिंग अ डायगोनल मेंबर टू द फ्रेम एलिमेंट. तो प्रॉब्लम ड्रिफ्ट का आएगा ही नहीं. स्ट्रेंथ इज व्हाट आई मीन. MRF सिस्टम में ड्रिफ्ट जहां गवर्न करता है फॉर अ CBF सिस्टम एंड अ BRBF सिस्टम ड्यू टू दैट डायगोनल एलिमेंट. अगर आप AK चोपड़ा के पहले चैप्टर में या दूसरे चैप्टर में कहीं देखेंगे जहाँ पे एक ट्रस एक एलिमेंट में डायगोनल एलिमेंट ऐड करते हैं, सो द लैटरल स्टिफनेस बाय एडिंग, आई मीन आप एक सिंपल स्टैट फाइल या ईटैप फाइल बनाएंगे और उसमें एक डायगोनल ऐड करके देखो, स्टिफनेस का वैल्यू निकालोगे तो स्टिफनेस इंक्रीजेस मल्टीफोल्ड. सो BRBF CBF में stiffness is not the main issue, as in the case ki drift criteria is not the main issue, but relatively between both systems, BRBF system is less stiffer, जिसकी वजह से drift once it goes into the non-linear range, both systems have to yield, right? Both systems CBF and EBF, BRBF have to yield in tension and let's say yield in compression also, or buckle in compression. So when it goes into non-linearity, a less stiffer system tends to have larger permanent deformation than a CBF system. That is the case. दोनों में है. It's not that in CBF system residual interstory drift is not there. It is there, but it is a lower value in comparison to what is the limit given by the code. That is the issue. The limit is making the issue a bigger problem.
Sir, but we can design BRB in such a way that it will follow the double stage yielding.
No, that is what we want. Na double stage yielding in the sense in tension and compression, it has to yield. It has to function the basic property. Like a CBF has to do, BRB will also do the same thing. It will yield in tension. It will go into multiple modes of buckling and compression. But that doesn't change. I mean, देखो, non-linear residual interstory drift is coming due to non-linear deformations leading to permanent set in the structure. If I have a less stiff structure like BRBF, which is also prone to have nonlinear deformation intentionally going to happen in the brace element or the BRB element, I will get some permanent set. The question is whether that permanent set will be more than CBF compared to BRBF. You know the answer, BRBF में ज्यादा आएगा. Problem कहाँ आता है? ज्यादा हो कोई problem नहीं. But if the code sets a limit of 0.5 percentage interstory, I mean 0.5 percentage interstory drift ratio से ज्यादा residual interstory नहीं जाना चाहिए, which system has more proneness to go beyond that? That is BRBF system. And once you design, you will understand that that value is like increasing. So you have to increase the stiffness in your system somehow by increasing, let's say, the size of the core element or by increasing the size of the beams or column element. You have to increase the lateral stiffness so that the बहुत ज्यादा नहीं vary करता, but such kind of interventions are required to decrease the residual interstory drift.
Yes,
It's a
sir.
question of designing, Rana and Rohit.
Yes, sir. Thank you. Thank you so much.
Yeah. Anybody else? I hope it was informative in terms of the both the systems, CBF, EBF. Now I request you can go through the code now without any fear and understand why these things are there and write to me directly if you don't understand a particular clause. I'm confident that if you have clearly understood what the thing is, you will have no problem in understanding the code.
सर जनरली शेयर वॉल बिल्डिंग हमें देखने को मिल जाता है, बट ब्रेस्ट फ्रेम बिल्डिंग बहुत कम मिलता है. इसके पीछे का कोई रीजन?
नहीं, दो रीजन है ना रोहित. दो रीजन था कि IS 800 का अगर आप 12th सेक्शन देखते थे, सेक्शन 12 देखते थे, it's only 1.5 page, right? So the design procedures were not clear, detailing procedures were not clear. So if you don't know how to design a structural system, let's say right now also, any of you might not be confident enough to design a CBF system in totality, right? But we know that if I give an element, wall element in E-tabs or a wall element in this thing, I'm confident of knowing how to design a shear wall rather than a CBF system, considering all these local and global analysis, right? Till 18168 came, Indians didn't have any kind of reference in the Indian code with respect to design of CBF. So that difference is there. Now that this code has come up, let's say we conduct certain sessions in terms of learning, like if you go to Steel Edu Forum, something like comes up. So once the designers and students like you learn how to design braces, the braces or the steel systems are much better than shear wall, because shear wall will increase your inertia in your structure unnecessarily. Even if you're retrofitting with shear wall or constructing a new shear wall, it's a tedious job in comparison to just going with some steel tubes and pipes. Cut karo, anchor karo, काम हो गया. And it adds less weight to the structure. And your grade of steel, I mean, ductility is like 100, 200 times more than what you have for RCC. Then your weight is less. Your strength to stiffness ratio, I mean, strength to weight and stiffness to weight ratio is also higher for steel. But since we don't know how to design it properly, that is why we don't use it in our RCC structure. Main problem.
Yes, sir.
Yeah.
Sir, I have a couple of questions.
Uh-huh.
The first is what I basically understand, that the bracing system is going to absorb the energy through the
Absorb
yielding.
the energy. Anandji, can you repeat?
The bracing system is basically dissipating the energy
Correct.
while reducing the seismic action.
Correct.
So it may be through the eccentrically braced frames or concentrically braced frame.
Only
Now,
concentrically.
Yeah. Now, in this context, what I want to know, nowadays we hear about the dampers, and many, even in Japan or in other areas, the dampers are also used effectively. So I'm not sure how the dampers are going to help in this context, or any further input on this from your
आनंद
side.
जी, इसमें इशू ये है कि डैम्पर्स का नाम में you might have heard about active dampers and passive dampers.
Right.
Active mein there is some control wherein when the earthquake comes in, it activates and kind of responds with respect to what is coming. These braces, EBFs and जो हमारा मोमेंट फ्रेम का जो बीम का ये है एनर्जी डिसिपेशन, they all come under passive dampers. Passive dampers में भी metallic dampers नाम में. You have viscous dampers, you have what do you say, the pendulum type dampers, tune mass control dampers, etc. उस category of passive dampers में braces, EBFs, BRBFs are all under the category of metallic yielding dampers. These are dampers, Anand ji. So their process is by yielding and compression, and yielding and metallic yielding. That is the name, metallic yielding dampers. It's like by yielding in tension, shear, or any other factor, or buckling in compression, they dissipate the energy and bring out an additional factor of damping in the system. Fuse element का benefit अलग है, उसके अलावा they effectively help in damping, increasing the damping in the system. So these are dampers only. These are passive dampers.
Okay. Now, why I want to ask this, because see, in one of your slide, I don't recall now, in probably last 3-4 slides, you're showing the eccentrically braced frames. And if I recall the diagram B, then in that there is a particular eccentrically braced frame where you mentioned that particular frame, not frame, the eccentrically braced system will be very helpful post yielding. It is very easy to replace it. I think
That Y-shaped one. The Y-shaped, correct. Where a chota link was below the beam element.
So that would be helpful to basically to you can say rebuild the structures or reconstruct the structure very quickly post earthquake.
Correct.
Is it something like that basically?
Correct. Same. उसी मामले में द लिंक एलिमेंट में आप मेटालिक पीस कुछ प्लेट अगर डालते हैं, तो अगर आप मान लीजिए कि आपका बीम एलिमेंट है, जैसे हम EBF जो नॉर्मल उससे पहले वाला डायग्राम था, वो सारा ये था कि whatever is my beam element, if I have a brace coming in between, then whatever is the length of the beam element which forms the link will get damaged during an earthquake. Now आप सोच के देखो कि अगर earthquake में damage हो गया, if I want to repair it, it will have slab on top of it, it will have beams there, it will have brace there. Replacement will be tough. But if I have a Y-shaped kind of a thing where my link is vertically connected, then I can have some connections there such that it can see. Removal is a word which is like easy removal is a very subjective word. So after an earthquake, kinks may be there, bolt may not even open. You may have to cut open everything. But relatively Y-shaped is where your floor is not, that kink is not affecting your floors too much.
Right.
So Y-shaped is like improving, but there also a metal has to be used. Shear, something in shear or in flexure, which like ADAS and TEDAS, you may be ADA system, TADS. All those are Y-shaped, eccentrically braced frame kind of a system only.
Okay.
Configuration and the way they dissipate energy is what creates the notion as eccentric or passive energy or metallic yielding damper.
Okay.
Yeah.
Fine.
Yeah.
Thank you.
Yeah. Okay. Any more questions? Okay. Tajul?
Okay. Yes, sir.
Okay,
Sir,
I think we can.
now if you wish to answer the questions in the chat box, it is okay. Otherwise, we can also prepare the answer sheet and share with the
we can prepare the answer sheet, Tajul. We can send it to everyone.
सर मेरा एक क्वेश्चन है, जो बकलिंग रेजिस्टेंट ब्रेसेस है वो पैसिव डिवाइस सिस्टम के अंडर आएगा या नहीं आएगा?
आएगा ना. यील्डिंग होता है वो टेंशन में, वो पैसिव डिवाइस ही है, मेटालिक यील्डिंग डिवाइस ही है वो.
तो ये एक तरीके से सर डैम्पर के तरीके से वर्क नहीं कर रहा है क्या?
कर रहा है ना. इट विल गिव यू डैम्पिंग. इट विल गिव यू डैम्पिंग. इफ यू फाइंड आउट ना, आप लिटरेचर में देख सकते हैं कि once you get the hysteresis curve, you can indirectly find out the damping that is provided by the system from the hysteresis curve itself. The hysteretic damping के नाम से आप search करिएगा, you will find out text and articles on it.
Okay, sir. Thank you, sir.
Yeah. I request people who are interested in steel structures to know more about design. Steel Edu Forum करके है, उसमें आप free में register करिएगा. There will be no fees ever उस केस में. And there will be topics on, let's say BRBF रहेगा. अभी currently it will come on moment frames, and then later on hands-on exercises भी आएंगे इस हिसाब से. तो who are all interested, anyone interested in improving the steel design this thing in India are all welcome to that particular site. Right. Thank you everyone. It has been a pleasure to have these two lecture everything. I'll ensure that जो भी questions है, Tajul kindly copy these questions and give it to me. I'll reply them.
Yeah, sure, sir. I have copied those already.
Yeah. Thank you, everyone.
Yeah. Thank you, sir. So thank you, everyone. So you might be knowing that this is the final session in our online training course on performance-based design, and it was great experience to share our knowledge with you all. And regarding the certificates, we'll inform you through the WhatsApp group. You'll receive within around 2 weeks or so.
सर स्टील का भी हैंड ऑन सेशन क्लासेस इन फ्यूचर अगर प्लानिंग करते तो बहुत बेनिफिशियल होता है हम लोगों के लिए
Sorry, actually, I couldn't get you. Could you repeat, please?
सर स्टील डिजाइन का भी हैंड ऑन सेशन अगर होता तो काफी बेनिफिशियल होता अगर
Okay, fine, no problem. We can plan another session in the coming months. So, whoever is interested, you can register to that course. Definitely, we'll be coming up with another session for that.
ओके सर
Okay. So, and one more thing, actually, for the last few sessions, I have not shared the answer sheet. Many of you have already asked, and what we'll do, we'll prepare the answer sheet for all the questions from whatever remaining sessions were there, and we'll make a single answer sheet for all those questions, and we'll share with you all. Okay. So other than this, before ending the session, if you have any suggestions or feedback regarding what you liked and what you have not liked, whatever you have anything to say, you can share with us so that we can improve in our future sessions if anything to come up. Okay. So we welcome you all to share your feedback, whatever you have to say. If anyone wants to say anything regarding anything, whatever you want to say, you can share. Okay, fine. If you want to write to us, also you are welcome. You can mail us whatever suggestion or feedback you have. You can mail us. You already have our mail IDs, mine as well as Professor Yugandhar Singh. You can mail any one of us. And
Right.
thank you once again. Yeah, anything? Someone want to say something?
Yes, sir. I think
Yeah,
definitely
please.
this was a very nice sessions you conducted, and many new you can say aspects were opened up. So this is a kind of a trigger, I should say, and definitely it will be helpful in the long run. So I'm sure that many such more sessions will come, and since currently we are a bit new, you can say, into this particular aspects, so it's probably we are not in a position to ask more questions. But I think as we understand the topic in more detail, definitely your advice and guidance will be very much helpful. And
Yeah,
thank
sure.
you.
Thank you.
Yeah,
Thank you for
thank you.
sharing your opinion. And yeah, that is actually thing because since past time you are learning this one, so you'll not be able to catch all the points or doubts. Whenever you start practicing with some real structure, you'll have lot of questions or doubts. And we'll open to share our knowledge, whatever questions or queries you will be having. Anytime you can contact us, either me or Professor Yugandhar Singh, you can come up with your queries. We'll try to solve your queries in the best possible way. Thank you.
Sure. Thank you, sir.
Yeah. So with that, let us close this session. And for regarding the certificates, or if any other information is needed for preparing your certificates, that we'll share through WhatsApp group. Okay. So thank you, everyone.